All right. And then we got AI companion is turned on. I don't know. They are so adorable. They're ridiculous. Betty doesn't like any of the other ones. And little bitty, poor Clara wants a family. All right. So let's do this. So where are we? We are here. Let me start this. Mixtape sessions, as always. GitHub. This might not take the whole day, because there's three papers. I was talking to Kyle, and we kind of both are in the same boat that some of the like extensive synthetic control kind of gets a little weird, and I don't find it super interesting. So I've kind of, I've tried to keep it pretty much at the core. So I updated it 9 minutes ago. I've been working a little bit this morning on the augmented synthetic control with staggered rollout, but I don't want to do it first. I'm going to do it I'm either going to do it second or first. I kind of wanted to just keep looking over it a little bit more, but I think we're going to do this matrix completion with matrix. So let me tell you what these are. Let me tell you where we are. All right. So we did this synthetic control, and if I just skipped right here, it might be I'm going to skip back, but this is kind of where we've been. So we had synthetic control by Alberto Abadi in the original 2003 Javier Gardeazabal study of the Basque country, terrorism and a truce and a bunch of other stuff, looking at the effect on GDP. And let me get this real quick. So a couple of the things about it, I think there's like, three things that we sort of learned. It was used for one single treated unit. There was no extrapolation. It was kind of really similar to like, nearest neighbor matching in a way, which also doesn't have any extrapolation. You just kind of try to find somebody that's similar and you match. They use weights to do it. The weights cannot be negative. They can be zero. And so since the weights are wanting to be negative, in order to minimize mean squared error, like getting there through negative weights is sort of like how these outcome regression models would do it. That constraint that it doesn't become negative creates a bunch of zeros. And then since the weights have to sum to one, it's just like reallocates the positive weights, kind of puts more on a few things, and you end up with what's called sparsity. Sparsity meaning a bunch of zeros. So we went through a lot on that. That was like a full day of synth on Alberto Abadi's original paper. And we were looking mainly at the issue of imbalance, because in the 2015 article, and I think also the 2010, we didn't discuss the 2015 article, which is another Alberto Abadi paper, but where it looked at the reunification of Germany. They've had this little quote, and we saw the quote where they were like, if the fit's not perfect, I don't know if they say perfect, but if it's not really good, maybe it even said perfect. If it's not really good, then you shouldn't use it. And if you don't have a very long pre-treatment time series, you shouldn't do it. So those were like the two things that they said, right? So you have to kind of decide at that point. You're like, well, I'm screwed. Like, do I just give up? And so there were two papers. There was the Christine Pinto and the Bruno Furman paper, where they demeaned it. They were like, we're going to demean it. And then the demeaning of it could improve, they could reduce some of that bias associated with the bad fit, but kind of still get you back to this. It could increase the variance. That was what was proposed originally. Again, this was like a very quiet literature. Theoretically, there were some applications that were done, but there was, except for Bruno and Christine, I don't think anybody was really working on it to modify it. New papers coming out. Ben Michael, Feller, and Rothstein have a 2021 paper. And what they do is they address that imperfect fit in the pre-trends using this bias correction method that Alberto Abadi and Hito Embeds had developed for matching with this outcome regression model where they basically get an estimate of the bias for the treatment group and the weighted control group. And then just like, they don't delete it out. I mean, they do delete it out, but like in that deleting it out, they like can rearrange it algebraically. And what you see is that the augmented synthetic control has some new weights, and those new weights are like slightly negative. They're slightly negative. Oh, I wanted to do one thing. Hold on. Okay. So there was imperfect fit in the pre-trends using bias correction and slightly negative. So what are we going to do today? What are we going to do today? Well, what we're going to do today, we're not really going to be messing with the non-negative weighting stuff anymore. That was what this augmented synthetic control was mainly doing. We're not really going to be messing with that. We're going to be messing mainly with this single treated unit. The single treated unit. And there's going to be two papers that we're going to do about that. This augmented synthetic control paper with staggered rollout, and then this matrix completion with nuclear norm regularization. So I'm going to go back. We're going to start with matrix completion with nuclear norm regularization. And I was going to, at the break, walk you through. I gotta like fix it. At the break, I've got 15 minutes. I just gotta like tweak this a little bit. I was gonna walk you through a paper of mine that was just published where we used it, and it's a bit of an awkward paper. It's a bit of an awkward paper because of like the timing of it came during this diff and diff renaissance. But if I can link this stuff up with if I can link this stuff up with the diff and diff literature, which two of these actually the rest of the papers today are kind of like linked up with the new diff and diffs. I think it can help make. I'm hoping that it can help demystify this a little bit. All right, so let's go ahead and start. This is a quote from the paper, the matrix completion paper here. And they're kind of talking about what the big idea of the paper is about. So they said the main part of the article, the one we're going to discuss, which by the way is in the thing, and it's here. So we go here, so you have it, readings, and it might be this one. I mean, it is that one, but I might have the new one here. Yeah. All right. So it was in a JASA. So it was a special issue. There was like a bunch of these that were published in JASA issue. Well, it doesn't list it, but it was a 2021 JASA. It was like in honor of synthetic control because the 2010 paper by Abadi was in synthetic control. And so here's this matrix completion one. And I want to say one of the other, I want to say maybe the augmented might have been in there too. Thought it was. Well, I'll find it. All right. So they say, main point of the article is about the statistical problem of imputing the missing values of Y. Once these are imputed, we can estimate the causal effect of interest, delta. To estimate the average causal effect of the treatment on the treated, which is the ATT, we will be imputing the missing potential outcomes, right? Now, that statement is, in fact, really not specific to matrix completion with nuclear norm regularization. It's not really unique to that. All of causal inference is doing this. It's just that some methods that do it are super explicit about it. Synthetic control is probably the most obvious imputation method, you're going to literally get a line and you're like, that's the synthetic control. That's the missing potential outcomes. Whereas if you do like regressions, you're like, where's the imputation that's happening in this? Or maybe if you did inverse probability weighting using propensity scores, it would be, or like anything times you're using these weights, for instance, or instrumental variables, it starts to be like not as obvious that you're doing some kind of imputation, but it is, because if the treatment effect is the difference between Y1 and Y0, okay, and if you just think about it for a moment, just like if we defined the treatment effect as Y1 minus Y0 and the average treatment effect as expectation Y1 minus Y0, and the switching equation selects either Y1 or Y0 depending on treatment status, then which means one of the two potential outcomes is always missing, then the only way that you credibly claimed to estimate a causal effect is because you must have imputed the other missing potential outcome, because you can't have a treatment effect without two potential outcomes. And in reality, you only have one, right? So it must be that the estimation of the treatment effect is actually behind the scenes estimating or imputing the missing counterfactual. All right. And so matrix completion does it. It just does it in a certain way, does it in a particular scenario, has various properties that makes it attractive. Okay. All right. All right. So let's keep going. So matrix completion with nuclear norm regularization, Susan calls it a synthetic control estimator. And so I teach it as a synthetic control estimator. But it starts to make you really wonder what the heck is a synthetic control estimator, because, well, no, that's not true. Susan and Hito and these others, they claim it's a synthetic control estimator. And the reason they claim it's a synthetic control estimator is they basically do this. They say that like the queen of all the panel estimators is going to be matrix completion. And nested inside it is two different kinds of like situations. One is synth, where one unit is treated. And then the other one is basically what they call unconfoundedness, where a lot of units are treated, but only in one period. And then something in the middle, and that is differential timing. So it's like they claim it's synthetic control because they're like, our method is really general and like unites all of these situations. There's Simba. Simba, come in here and just chill. So that's what it's going to do. It's going to unite. And there's a lot of language, and we see this again in the augmented. So I'm going to kind of not to go too fast. It's going to unite single period, single unit. Single unit treatments is the synthetic control historically, the previous thing. Single period treatments, that's not stuff that we've studied, but that would be like an RCT, for instance, where units are treated like on day one and then like another units are not treated and you just compare them, right? And so, or it could even be well, I wouldn't, I guess it could be a difference in differences too, but like the unconfoundedness assumption and the synthetic control are, I've been up since 3:30 because of that cat, because of Simba. Anyway, so it's going to use imputation, and the reason why it's called matrix completion is it's going to use this thing called a low rank matrix. It's going to impute these missing counterfactuals and construct estimates of the average treated on the treated. All right. Nuclear norm regularization is used for that imputation, as opposed to lasso or elastic net. And it can accommodate a bunch of different timing setups where parallel trends may not hold. Now, I have struggled to exactly come up with a data generating process where parallel trends doesn't hold, but matrix completion does. And so I've not, what I'm going to do is show you it applied to situations with it. I'm going to show you one where I applied it to a situation with parallel trends. And that way you can at least kind of see, okay, this is something I could do with differential timing, right? That I can do. And at least then you can sort of try to find whether or not there's alternatives. I have yet to really find one where but you have to kind of work with these simulations. All right. So here it is. So what is a matrix completion? It's gonna go back. Might even be better to do this first, and then we can kind of jump back, right? So the history of it goes back to the Netflix competition that started in 06. It's probably older than this too, but this is like when I think it became famous. So there's this like open competition, and it was not used for causal inference originally. Matrix completion wasn't. It was used for prediction. So there was this open competition by Netflix prior to streaming when you would get the physical discs in the mail. And they had this thing where they said, if you can improve the model by reducing the root mean squared prediction error by 10 points. Now, I don't know what the units were, but I think that was actually not trivial. So it was like, to get it down by 10 points, then you'll get $1 million. That was in 06. And it just invited a lot of competition. It was a ton of advertising for Netflix. It was kind of really cool and exciting. I was in grad school. I didn't study predictive modeling, so I didn't really even know what they were doing. But basically what they did was everybody was given a database of ratings of movies you had seen and of movies that people had seen. And then there was like a holdout database. And the holdout database Netflix had back home. And so you could fit the model on your database. You could like separate it into a training model and a validation, a training data set and a validation data set. You could run elastic net, you could run lasso, you could run sort of gradient, what are these things called? Gradient boosting or whatever. So like you could do all kinds of stuff. All right. But you had to submit your code to Netflix. They'd run it. And then like regularly, I don't know how often, but they would regularly then update like a leaderboard. And they would like show the leaderboard. And there was a lot of really quick progress. I do remember that there was like, I had read in the newspaper that there was like really, really quick progress where like within several months, they got it down, teams got it down 5 points. And it was like people, I mean, it was really kind of cool. It was like people from MIT, like faculty. And then it was like everyday people, like just like a normal person would like go home and they'd work on it. And but it was like really big advances, probably with like, probably with a bunch of regularization or something. And then it got really slow. And the winner was announced in 09. And I believe the winner, this way I've written it up anyway, the winner was some sort of composite model of a lot of things, and matrix completion was in there. Matrix completion is a part of the winner. So it was this gigantic, sparsely populated matrix of movies, you know, and it would be stuff like this. Guy likes Napoleon Dynamite and The Matrix. They meet somebody, you know, but then here's somebody that only likes The Matrix, but they like a bunch of stuff. What, you know, should Netflix recommend they watch Napoleon Dynamite? There is a paper I saw that said that this matrix completion, though, you know, even though it was filling that in, it was kind of causal in a way, because they were like, if I show you Napoleon Dynamite, will you like it? So that's kind of a causal question. So so like here's the way matrix completion gets set up. They set things up differently than the way we've been setting it up, because we haven't really played around with any matrices. I guess we did a little bit with, yeah, we did, I guess. We did with synthetic control, but this is gonna be a little bit, this is gonna be a matrix in the panel dimension, okay, where we had multiple units and multiple time periods. And so this here is a matrix of Y zeros, all right? Y zeros. This is unit 1, unit 2, unit I. And unit 1 is observed, well, unit 1 has a Y0 that goes from period 1 to period T. And unit I has one that goes to period T. Okay, so it's a matrix of potential outcomes. You have a matrix of Y1s, you have a matrix of Y0s. They're real. They're not necessarily realized, but they're like what Don Rubin calls real, but they're ex ante fixed but unknown. Okay, ex ante fixed but unknown, because you don't know which of these, you don't know if Y0 or Y1 is going to occur until the treatment is assigned. So we're going to have a treatment assignment, and the treatment is going to assign the treatment in the last period. And I think I might have a mistake here, but it's going to assign the treatment in the last period. Yeah, I did. So I've got everybody treated here, which I didn't. Well, it's fine. We got everybody treated. I guess that's going to be okay. So everybody gets treated. Now the matrix is incomplete. Okay, why? Because of the switching equation, because of treatment assignment, these are gone. Because now the only thing that is observed is Y1. So you've got this like matrix of Y zeros, but it is incomplete, right? It is incomplete. Matrix completion is simply going to complete the matrix with nuclear norm regularization. It's important that you say nuclear norm regularization, because there's many ways you could complete the matrix. And this is only going to be based on a particular regularization. All right. So what you're going to do is the method will just simply use patterns in the data, patterns in the Y zeros, both across and down, and then use those patterns to impute what that is. We'll do it too. We'll do it with the in a minute with the data set that I like to show people. Once you have those, once you have these right here, since you know you now have imputed Y zeros, and in reality, you have the Y1s, calculating the individual treatment effects is just Y1, the real one, minus imputed Y0. That's an individual treatment effect. And then you just have an aggregation scheme. You just average it up. Okay. So important points about synth imputation versus diff and diff imputation. The assumptions in diff and diff use parallel trends to do the imputation. Because for those of you that have taken the diff and diff workshop, there is this, you know, day 3 was actually day 2 and day 4. On day 2, we were doing the covariate diff and diffs, and we discussed this Heckman, Ikamura, and Todd 97 paper on job training programs, program evaluation. And in it is a section where they do diff and diff based on covariates, and they have an outcome regression model where they impute the missing counterfactual. They use only the control group, And then they use this method to, you could use a regression, but they've got this outcome regression model to impute the missing Y zeros for the control group. And the reason why they do it, and then Borisov et al., we discussed that on the 4th day with the differential timing. Borisov et al. Do the same thing. They both do an imputation. What allows them to do the imputation? It's an assumption that and the assumption is very simple, that the change in Y0 that we observe for the control group is what would have happened for the treatment group. And so when you use changes in Y0 for the control group and you find what that change is, then you can just use that change for the treatment group from some baseline to a later period, and you get it. You can either do that doing what Heckman, Ickemer, and Todd do, or they have this non-parametric method based on the covariates, or you can do what Borisov et al. Does, where they estimate fixed effects and then just use those fixed effects to do an imputation. Okay, you can do it either way, but they're based on a parallel trend. You can't, that's not inside the inside this scent imputation is not a parallel trends assumption. And that's kind of the theme of today. So you can't really compare these two methods because it's like, you should use diff and diff if parallel trends holds, and you shouldn't if it doesn't. And you should use these methods if their assumptions hold, and you shouldn't otherwise. So, like in the most abstract sense, use the tool that the tool is designed for. So you can't really like compare them. That said, it's very abstract levels of assumptions. So it does become kind of hard to really say, they're both like untestable. So it kind of gets a little challenging to say what you should be doing. So we're going to be, so navigating between them, between these synthetic control estimators and these diff and diff estimators, is probably going to get even more complicated now. Because, and the reason why it's going to get more complicated is because as we're going to see, the use cases of today's estimators are basically the identical situations where you use diff and diff. And so since it's like the use case is identical, it's going to all come down to these identifying assumptions. And these identifying assumptions can be, not the easiest thing to articulate. And it's not clear if there's any available tests beyond the event study to justify their use. And I don't myself know what to say, because when you see these methods presented, I think probably the only thing I would say here is that, one of the advantages that you get from the synthetic control is if you've got a long pretreatment time series, then that can help with the imputation. And that's not really something that's going on really with the diff and diffs. So that would be like the only thing I can really think of. But putting that aside, you're probably, it is important probably that you learn some of these sense things, because the gap, in their use cases is getting really small. So there's these two literatures that they have in mind. And at first glance, there's like nothing that connects these two literatures. There's this unconfoundedness literature or selection on observables. That's the propensity score literature. That's anything that has to do with covariates, regressions, nearest neighbor matching, propensity scored, coarsened exact matching. These are all unconfoundedness based estimators. Now, they're not usually panel, though, is the thing. They're not usually panel methods. They're like, usually if you look at them, it might be a cross section. Okay. Synthetic control is a panel estimator. It's one of the causal panel estimators. And we talked about it yesterday. And what they're going to do is they're going to say, well, our our method, this matrix completion with nuclear norm, it's gonna net. That's what the phrase is like. It's gonna nest both of them. Both of these here and here are just going to be special cases of matrix completion. That's the claim they make. I'm not saying I don't agree with it. I'm just saying when I saw them present it to Alberto Abadi, I thought Abadi made a little face. So I'm not positive what to say to that. So they're conceptually different. They exploit patterns in the data in different ways. So unconfoundedness methods like a propensity score, okay? It assumes that patterns over time are stable across the units, but Synth assumes that patterns across units are stable over time. Okay, so they're kind of like so any kind of like patterns that, so Synth assumes that. Why would you say that Synth assumes that? Because once you get those weights, those vector of weights, they're fixed, right? They're fixed. And California is all, or like Illinois and California, if they've got weights of like 0.5 and 0.5 for Texas, it's assumed that they'll always be like that, right? That's the idea. The idea with synthetic control is that, well, once you've settled on that pattern, on those controls, it's stable over time. And unconfoundedness doesn't make those assumptions. It says though that that the patterns over time are stable across the units. So what's going to happen here is that the regularization method that's going to be used, okay, it's not going to be elastic net or lasso or ridge. Regularization that they're going to use is this nuclear norm. And what it's going to do is it's going to like take advantage of both of those, okay, and ensure a low rank matrix needed for sensible imputations. You're going to get back to these factor models that we kind of discussed yesterday that are kind of, whereas diff and diff has a parallel trends assumption inside of it, you don't actually see it. That's the identifying assumption. Inside the synthetic control is a factor model assumption. You don't see it. You know, you're not working with one, but you're basically saying that if you have a long enough pretreatment time series, then you've been able to fit weights that model those factor loadings. Okay. And so this factor model and this interactive effects model, the observed outcome as the sum of a linear function of covariates, and this is how it's done. Factor model is assumed to be a sum of linear function of covariates, an unobserved component, okay, just like before, but this unobserved component is going to be this low rank matrix. Plus, there's going to be some noise. All right. And so estimates are typically based on minimizing the sum of squared errors, given the rank of the matrix of those unobserved components, and the rank itself ends up getting estimated. Nuclear norm regularization is going to be used to do that imputation. And you're going to get, after that, once you do the imputation, it's going to look a lot like a diff and diff. You're going to get event plots. You're going to get event study plots, sort of. And you're going to get overall average treated on the treated using those estimated treatment effects. All right. So 3 contributions. I'm only going to discuss 2. Formal results. It's an econometrics paper, so everything's about the formality of things, asymptotic properties, and so forth. You're going to get these formal results for non-random missingness when the block structure allows for correlation over time. You're going to show unconfoundedness and synthetic control are both matrix completion. They're both going to have the same objective function. They're going to have different like constraints. And the synthetic control has those non-negative weights as its constraint, and matrix completion doesn't have that. It has regularization to characterize. That's like their kind of way of seeing the similarities. And then they're going to apply it to 2 data sets. But I didn't really think that was as interesting. Plus, we're going to do that a few times. So lots of new and old terms, lots of new terms, lots of old terms. And I'm going to just go through all of it kind of slow. So we've got these terms: unconfoundedness, vertical and horizontal regression, fat and thin matrices. These are the two right here that you're probably unfamiliar with. This idea of a vertical and horizontal regression. Okay, that's new to a lot of people. It was new to me. I didn't know there were two kinds of regressions that you could run in a database, but there are. We usually run horizontal regressions. You know, I am regressed on my own background characteristics. You're regressed on your background characteristics. And that's called a horizontal regression. So they're going to talk about something called a vertical regression. And then they're going to talk about different sizes of the matrices. And so they're going to define the matrix in terms of what's called a block structure. And then in that block structure, they're going to describe where the missingness occurs. All right, we're going to discuss these concepts related to the direction of the restriction of the regressions. So unconfoundedness. This is Heckman and Robb call unconfoundedness selection on observables. Rubin calls it unconfoundedness, means there's no confounders. All the confounders are in the data. You know what they are, and you're controlling for them. Okay. The historical program evaluation literature typically was estimating average treatment effects, assuming unconfoundedness. So like, for instance, Bob Lalonde's 1986 paper, Degia and Waba's 2002, Smith and Todd 2005. Anytime someone's running regressions with controls, they were part of that literature. Okay, they were assuming unconfoundedness. That's a proof that Rubin and Imbens and Rubin show in their book, their 2015 book, which is around here somewhere. But the focus, kind of stepping back, in the unconfoundedness, in the block structure that they're going to show, is that, you know, unconfoundedness is an assumption, but the block structure that we're going to look at is where you've got a missing potential outcome in the last period, the post-treatment period. Okay. So in Lalonde, the group, the National Support Work is it called National Support Work Demonstration Group? I think it's called National Support Work. So it's this RCT that was done, and Lalonde dropped the control group and replaced it with a random sample of Americans. So you don't observe Y0 for the treatment group in 1978. You observe it in 1975, and you have some pre-treatment data, but you don't observe it in 1978. Why? Because they were treated in 1978. It's a 3-year program. Once you're in it, you're treated. So I don't observe your Y0, your earnings, in a world where you weren't in the program. I observe for the treatment group Y1. All right. So the last period, 1978, is this like missingness. All right. So in the unconfoundedness part of this paper, they're always talking about a simple setup where the last period, some of the units are treated. Okay. And they call this single treated period block structure. Single treated period block structure. It is not the synthetic control setup, because the synthetic control setup is going to be a single unit block structure, single treated unit block structure. But here's the unconfoundedness one. Last period untreated. All right. Here it's, I probably could have had some of these guys to be a control group, but the idea is that they're only missing in the last period. They're only missing in 1978. So this is the sense. So that was single treated period, last period, unconfoundedness block structure, single treated unit block structure. One unit is treated in some period in time, and this is the donor pool. right? So this is the synthetic control design inside a block structure, and they're describing it. Differential timing has a block structure too. Like a group of states gets treated here, units get treated here, units get treated here. So these block structures can accommodate like pretty much everything. On the one end, everybody's treated, somebody's treated in the last period. On another end, one unit's treated, and then in between, multiple units treated and multiple units treated at different points in time. It's like the block structure can handle all those things. What we're looking for is an estimator that is general enough to manage all of them. And matrix completion with nuclear norm regularization is an example, all right? So what we got to do next, so now that's describing block structure, right? The next thing is we got to describe the matrices in terms of how many rows and how many columns. So like here, like we've got a block structure related to the missingness patterns, but now we're going to talk about the matrices with how tall and how wide they are. And if they're really, really tall, that means there's a lot of units, but not as much time. So like the Lalone study would be an example of like a really tall one. They're going to call it thin, but like a really tall one, because in the Lalone study, Lalone 1986, you had 185 units in the treatment group and 16,000 units in the control group. And so it was very thin because you only had 1978, 1975 in the original Lalone paper. You only had 2 years. In the Deji and Waba one, you had 1974. So whether it was 2 years or 3 years, it was still much smaller than the number of rows. And so that's a thin matrix. And then there are, these fat matrices, and I actually have not seen very many of these, where this is where you have way more periods than you have units. So I guess mine yesterday, so maybe mine was, so my Rhode Island project was 1965 to 2009, and then so 2009 is the original, 2009 minus 1965. So that's 44 years. We have 51 state units. So it was still, still N greater than T. Okay. Maybe I don't think I dropped any. So it's pretty hard. It's pretty hard to get it with state panel data. It's going to be pretty hard to get it. Yeah, it's going to be pretty hard to get it because you would have to have like fewer units. All right. But if you did, it's called a fat matrix. If you did have it. And what I had was probably more like a square where T is approximately equal to N. And that was probably what I had. And I could have had a completely square because we could have gone back to 1960 in the data, but the New York data was messed up from 1960 to 1965, so we didn't. But we'd have had about 50 years and 50 units, pretty much. That would be a square matrix. All right. So we got missingness. I'm going to summarize that. So we got block structure and missingness, right? We had single treated unit, that's the cent. Single treated period, that's unconfoundedness. And then do we have differential timing? Yeah, differential timing, where it was like, could have multiple units, multiple treated units with or without differential timing. So that's the block structure. Then we had the size of the matrices, the size of that Y0 matrix. And you had thin, which was n greater than t, way more units than time. Then you had fat, which was t greater than n, way more time periods than units. And then you had square, n approximately equal to t, around the same number of units as periods, right? So then we have one more, regression. Now, what regression is doing, regression is the estimation of the weights, okay, of the weights in this. We're going to use this penalized regression to do it. But they're first going to separate out different kinds of regressions, right? Different kinds of regressions. First is the horizontal regression. This is normal regressions, okay? Regress, left to right, left to right, right? So you got like Y regressed onto X. That's horizontal. Vertical regression is this is the cent regression. This is the cent regression. Regress units onto units, outcomes onto outcomes, get coefficients on the units as opposed to the covariates. And cent constrains those coefficients to sum to one, and not be negative. All right. Augmented cent allowed for did that penalty term. But vertical regression is like literally like, okay, imagine I was running regressions of me onto Resham or me onto German. Okay, me onto German and Caesar, and finding correlations of similar groups from the regression. All right. Now, cent is the thing you do with vertical. All right. And horizontal is the thing you do with unconfoundedness. So unconfoundedness has that single treated period. So with unconfoundedness, just put in their word single treated period. It's about the period. All right. Single treated period block structure with a thin matrix. Uses a large number of n units to impute the missing potential outcomes. Like that's a recommendation that comes out of nearest neighbor matching. Because one of the reasons it comes out of matching is that unconfoundedness in combination with common support will let you estimate causal effects. Common support will fail because the data set is too small. And you won't have, the exact dimensions of the covariate won't hold in both groups. So you need a large N to do unconfoundedness-based methods. So you, and that's horizontal regression. The vertical regression appears to, and I don't know these papers super well. The Duchenko and Embens paper, Duchenko ends up graduating from Stanford. He was an Embens student. He goes to work for Google. This paper just gets kind of orphaned, and a lot of the principles just get kind of distributed. They get distributed elsewhere, all right? And Duchenko and Embens, what they do, and Pinto, they show that this is where the vertical regression stuff came from. They show that cent actually can be interpreted as regressing the outcomes for the treated prior to treatment onto the outcomes for the controls in the same periods. And it's as though you're going up and down. And then you're placing restrictions on what the coefficients can be. And if you had absolutely no restrictions, you could have negative weights. You could have some unit, they could be anything, because the regression a purely unconstrained regression would just be simply trying to do the best linear prediction of the outcome, and it would allow for negative weights. It would allow for that extrapolation. What Abity does is he puts constraints on what those coefficients can be. They can't be negative. They have to sum to 1, right? And so synthetic control can be reinterpreted as a vertical regression. If once you see it that way, then it opens up the possibility of different model specifications. And that's where Duchenko and Embens proposed adding an intercept. And the reason why the intercept was important, and it seems so trivial, but see, like what was going on with Abity, it was a few things actually that was going on. One was, if it's a vertical regression, first of all, the coefficients and the coefficients cannot be negative and they have to sum to 1. Okay, so that was one thing, but that didn't guarantee that, those, when you took those coefficients and then you like predicted from it, if you could not, there's no guarantee that would do a good job of reproducing the time path of the treatment group. And it could be too big, it could be too low, you could have these outliers. So Duchenko and Embens, since they were thinking of it as vertical regression, they were like, oh, look, Abity never had an intercept in this because he wanted everything to be a nearest neighbor. What if we put an intercept in? Well, once you put an intercept in, you can have like a synthetic control that is like the messy synthetic control. He's just below messy. He's below him, but he shifts up because of the intercept. All right. So once synthetic control was framed that way, that was like their hook to get around that convex hull requirement. And they did it without putting any negative weights in. All right. It's actually pretty interesting. So both horizontal and vertical regressions, as you can kind of imagine, horizontal regressions are exploiting certain patterns in the data. Okay. And vertical regressions are exploiting certain patterns in the data. Okay. So, well, the horizontal regression, that's their way of saying unconfoundedness. And the vertical regression is their way of saying synthetic control. So what they do in the paper is they consider an approach that's going to allow them to basically do both. Do both of them, exploit stable patterns over time, stable patterns across units. Okay. So matrix completion with nuclear norm does both of them. And they're also kind of going to do the same thing again in their synthetic diff and diff. So they're going to model here, if you think back to what we were looking at with that augmented synthetic control, or even with Abity, we had a factor model. This isn't quite a factor model. What we're going to have is the potential outcome, y, is going to be determined by this matrix and this error term, this noise term. Here's the unconfoundedness part coming in. So this error term is just going to be a 0, conditional on the low rank matrix. And they kind of say, well, what is it? It could be measurement error. So you have this complete matrix L star, and then you've got this exogeneity assumption, this 0 mean conditional independence. So I wrote this down. I want to just real quick, what is the purpose of this assumption here? Because it shows up in a different paper. This sub-Gaussian random variable, all right, this sub with scale parameter sigma, okay, so the error is independent of L star, right? That's that unconfoundedness assumption. And the elements of the error are sub-Gaussian random variables with scale parameter sigma, or sigma sub-Gaussian. I'd never heard of that before. What it does is it places a restriction on the tail behavior basically doesn't give you fat tails. They're not going to have any fat tails. That's the way the assumption is, right? So they're basically assuming this like normality, but no fat tails in this error term. This is kind of like a dumb slide. I was trying to I used to try to explain this in a way that might understood, but I was just kind of saying, there's lots of ways that you could do imputation. And you could minimize the sum. I don't think so. I don't think so, Taha. You can not really you can't really test unconfoundedness either. And this right here, this is an error term. It's unobserved. So I'm not really sure what how that can be tested. There might be actually, I mean, I'm not positive. Every time, the story of causal inference is people come along and figure out how to test stuff. So I'm not really sure. But you need it. So how are we going to do the regularization? I went to Stanford and I presented this paper that I'm going to show you guys. And I had office hours with Embens, and I was talking to him about this paper, and I was like, why do you use this nuclear norm regularization? I've literally never heard of it until I read this paper. I know people have heard of it. It has some history in math. I think it might even have something to do with Terence Tao. And they were like, well, he said, well, you could use other penalties. You could use other forms of regularization. You could minimize the sum of squared differences. You could use elastic net. You could use ridge. You could do all these things. A lot of them will spit back nonsense. And one time in our paper that uses matrix completion, we went through, or my co-author went through and found like the original, or there's a well-known matrix completion estimator, not the nuclear norm. And he ran it. It was really kind of wild. He ran it and everything came back with zeros. And I said, well, and I pointed it out and I said, well, it says in the paper, if you do that, it'll do that. And he was like, oh, okay. So we had to use Embens' actual code. So if your objective function doesn't depend on the L star, the estimator just spits back Y and you get zero treatment effects, because then you'll just get Y. It'll predict Y, and then you'll get Y. You'll get Y. You'll predict Y. Y minus Y is zero. So it won't be able to do it. So they add in a penalty term to the objective function. But even then, not all of the penalties that you could put on there, like lasso or elastic net, not all of them do well. And so some of them will spit back nonsense, or some of them will just they will take an eternity to do anything. And it'll matter whether you regularize the fixed effects. All right, so I'm going to take a break real quick. 15-minute break. We're going to try to be pretty disciplined about the break. So we'll be back in 15 minutes. So come right back. All right. Here's the estimator. It's a regression, but this is their notation. L star. They have here this let's see, where's the fixed effects? Here's the time fixed effects. And then these are, so this one here, here's the time fixed effects, and here's the unit fixed effects. And this is Y minus the L. And so you're minimizing this entire norm here. And with this penalty term, and then you're solving for the low rank matrix, the fixed effects. And the fixed effects they make a big deal about the fact that the fixed effects are outside of the penalty. The penalty will be the nuclear norm, but notice the fixed effects are outside it. You'll not really be dealing with this, but this is just important that you, I mean, know these kinds of things. They say you could subsume them into the L matrix that you're estimating itself because the L matrix is in here, but they say don't do it. The reason they say don't do it is that you've got a lot of observations. You can get the fixed effects. You can get unbiased estimates of the fixed effects, so get them. And apparently, historically, the everything with matrix completion was inside the penalty, but they don't do that. You choose the penalty using cross-validation. It's fast. Here's like the advantages. Um, so some of it's practical. It's a very fast procedure. There's these programs that will do it in like a blink of an eye, and others won't because of the large block size, because of the thin or the large number of N or the large number of T. This is why they're saying this can do it. I made these kind of comments here. So once you get it, what are you getting? So you once you've solved for L, okay, what do you get? You can now impute, once you know L star, once you have all of these, you can impute L star. And if you know L star, then you know Y. Okay. And you're using the untreated units to do this. Oh my gosh, you're using the untreated units to do this. All right, so the penalty will be the nuclear norm fraction. I said that. So this model can be used for differential timing. At the moment, I've not seen anybody. Well, there is an undergraduate that sent me his undergraduate thesis, and he compared all of these like major robust diff and diff estimators with matrix completion. And I don't remember, and I think it wasn't like it was like most of the time it was it was pretty similar. So it's going to come down to these parallel trends assumption versus these factor models. But I think these factor models are oftentimes in reality, they're fixed effects models, and fixed effects models will give you parallel trends. So they appear to be it appears to be pretty similar. But you can historically get it through GSynth. All right. In Stata, it's called FECT, but GSynth had some complaints. So our GSynth error and I had a paper that was in the field. I had a paper that actually was one day this quit working. I'm trying to find out where it is here. Anyway, there was like in here, there was like all of a sudden one day GSynth quit working. And unless you put in a random variable. So you had to like you had to have this like covariate matrix, and if you didn't have any covariates, then you had to just put in a covariate that was just a random variable, and it had never been like that before. So so I would say watch that a little bit, and maybe they fixed it, but well, it looks like I don't know. So what I'm going to show you, me using the FECT command. Okay. Okay, so let me show you this. Some of you have seen me do this, but I want to show you the bias of the two-way fixed effects estimator. Okay, so I'm going to generate two pieces of data, okay, to kind of help illustrate something. I'm going to illustrate two pieces of data. I'm going to generate a differential timing situation. I'm going to generate a differential timing situation. And in this differential timing situation, there's going to be four groups, 1, 2, 3, 4. And data is going to go from 1980 to 1990. And I'm going to have four groups, group in 86, 92, 98, 04. Prior to each of these cells is a treatment effect. It's an average treatment effect. There's 250 firms in each of these. So I have 1,000 firms. 250 were treated in 86, 250 in 92, 250 in 98, 250 in 04. All right. And before you're treated, there is no treatment effect. When you are treated, depending on which group you are, you either get 10 and it stays 10. So it's like so basically it's like, you get treated in 1986 and your earnings go up by $10 and they are always $10 higher than they would have been. So it's not that it's going up 10 more dollars every single year. It's an average treatment effect for that year. 10, 8, 6. Then we're going to do dynamic differential timing, dynamic treatment effects. Okay. And it'll be a person who goes and in the first year, they're treated in 1986. In the first year, their treatment effect is a 10. Second years, it's a 20, 30, 40, 50, 60, 70, 80, 90, so forth. Okay. All right. So let's make that data. Okay. So I'm going to have here 40 states, 25 firms per state. It's going to give me 1,000 firms and 30 years of data. So I got here count 30, 25, 40. Display 30, 25, 40. It's 30,000. And that's how big our data set is. Okay. You can see here what I've got, this firm variable. It's a fixed effect. We're going to use it in just a minute. It's a fixed effect. This is the year. This is the state. This is the year. And this is the firm identifier. This is firm number 1. And I've got 1,000 firms. And then I've got this counter. And the counter is just counting how many years there are. Goes all the way to 30. And it starts over. Okay, and there's firm 2. And firm 2, she has a different fixed effect. Okay. So now I'm going to get this one right here. I'm going to do my constant treatment effects. First, I'm going to generate these 4 groups. Okay. So I'm going to generate these 4 groups right here. So I did that according to their treatment date. So let's do list in 1 to 10 again. So this is a treatment group born in 1986. Whoops. So that's this one. Okay. And since in the data it's 1980, which is before 1986, that one's not treated yet. But in 1986, it's treated. So it'll be treated. Okay. So it's treated, but we don't have any of these colors yet. So let's generate the data. All right. So I'm going to generate these data right here. I'm going to use these variables. These are just variables I've made. I got a TE1 called a 10864. groups 1, 2, 3, 4. I'm going to clearly use 10, 8, 6, 4 in just a minute, but I haven't done it yet because I haven't made any outcomes. So I'm going to have my model is going to satisfy parallel trends. Okay. It's going to satisfy parallel trends. And so all of the firms are, this also will satisfy unconfoundedness because each of the firms will have like their own, identical trends. The change in Y0 is the same for all the firms. All right. So that's what it's going to follow. So everybody's Y0 is going to start at their fixed effect, and then it's going to go up by N plus E, but E's on average 0. So it's everybody's Y0 is just going to go up by N. Okay. All right. So I'll do that. So now we're going to have two different variables. All right. Y2 is this one, constant, 10, 8, 6, 4. Here's how it works. Fixed effect plus N. Are you treated? If you are treated, then you're going to get either a 10, 8, 6, 4. If you're not treated, you get nothing. So if it's a 0, then it's nothing. Then it's just Y0. But if you are treated, everything after will be Y1. Okay? And for this one, that's my dynamic one. And for my dynamic one, I'm going to have a firm fixed effect plus a counter. If you're not treated, that's a 0. So then it's just Y0s. But if you are treated, then it goes up by 10, 8, 6, or 4, depending on which group you are. It goes up by 10, and then this gives you multiples. All right, so if it's 1986, for instance, okay, it's the year of treatment. You were treated in 1986, and it is 1986. That's a 0. 0 plus 1 is a 1. 1 times 1 times 10 is a 10. So it'd be 10 in that period. If it was 1987, 1987 minus 1986 is a 1. Plus a 1, that's a 2. 2 times 1 is a 2. 2 times 10 is a 20. So that becomes a 20. And that's how it works for everybody. Okay? So I've done that one. All right, so let's look at some stuff here. On average, treatment effect, when I'm just looking at the constant, when I'm just working with the constant here, the average is a 7. And I'm going to run a two-way fixed effects model. And I'm going to get a 7. So the average treatment effect here, okay, it's like depends on how it's aggregated, but the way two-way fixed effects works those of you that have been in my diff and diff class, the two-way fixed effects has some weird funky weights on it. And even though the average of all of these is an 8, what two-way fixed effects does is it sort of suppresses that one, and then kind of inflates these two through this variance weighting, and it's a 7. And that's what it finds is a 7. But if I go over here to the dynamic, and I just average all of these, okay? If I just average all of these, then I get an 82. Get an 82. All right. So let's see what happens with two-way fixed effects. I'm going to hide it. What happens to two-way fixed effects if I estimate the exact same model? And notice how both outcomes had a same fixed effect, same counter, same error, no covariates, no omitted variable bias, Nothing like that. One of them has dynamic treatment effects, the other doesn't. I'm going to run that one. The truth is an 82, and I get a negative number. And we know from the diff and diff literature, all right, we know from the diff and diff literature that if you have differential timing, all right, units getting treated at different points in time, which is what I have here, and you have dynamics in the treatment effect, then this model right here is biased. Okay, it's biased. And it's biased by the parallel trends assumption, but we have parallel trends. And it's biased by a negative weight on the dynamics. So if we have dynamics here, they'll get subtracted from that 82. And if the dynamics are large enough, they'll be completely gone. All right. So what we're going to do is we're going to do matrix completion. Now, the thing about matrix completion is technically you need to only have periods of time where you have at least some untreated units, okay? There has to be periods of time where you have at least some untreated units. So I'm going to have to drop this period right now. Okay, so I'm going to drop if year greater than 2003. All right. Now, if I drop the years greater than 2003, then I'll get a 68.3. Okay. But why do I have to, why do I have to only have untreated units? Because you're using patterns in the Y0 to fill in the missing counterfactuals. So if everybody is eventually treated, then, you can't use it. So like technically, actually, I need to, at this point, everybody's treated. So I need to have like a little bit further back. So you have to have at least some untreated units in a period. All right. So I'm going to run it and it's going to do a bootstrap. So it's going to be FECT. So I should definitely SSC install, FECT replace. Oh. You gotta do a few of them. I've already installed them all, but I should put this all at the top. I'll put the newest package in just to be on the safe side. Okay. So it's fact, and I can't remember why it's called that. Practical Guide to Counterfactual Estimators for Causal Inference with Time Series Cross-Sectional Data. And it does a lot of stuff. It's not just matrix completion. FECT implements counterfactual estimators in time series cross-sectional data analysis, which I think is their way of talking about panel data. These estimators first impute counterfactuals for each treated observation in a time series cross-sectional data set, panel data set by fitting an outcome model, fixed effects model, interactive fixed effects model, or matrix completion, using the untreated observations. They then estimate the individualistic treatment effect for each treated observation by subtracting the predicted counterfactual outcome from its observed, meaning it's only going to give you the ATT. Oh, there's a placebo test. Okay, I don't know about that. So what do we do? Matrix completion. You can put covariates in. We don't have any covariates, but you can put covariates in. All right, so let's run it. And so drop if year greater than 2003 must use a matrix of Y zeros only. So drop the fully the fully adopted periods. So we did that. All right, we're going to run it. Quietly fect Y, comma. Oh, and so the estimated ATT is 68.33. Okay. So okay. All right. So let's run it. Quietly effect Y, that's the outcome. We're going to be working with the dynamic treatment effects. Y. Treatment, that's the treatment indicator. Panel identifier, firm, panel identifier, year. We're going to do matrix completion. And we're going to use cross-validation to get the, for that penalty term, standard errors are going to come from the bootstrap. See how fast it goes. I don't remember. I don't think it's fast. While it's doing it, I can show you that we did have, let's see. No, I don't have it in here. So I will show you. Well, we could see it. That would be a good exercise. While that's doing it, the G-synth. G-synth was originally based on, and I am drawing a blank. It was originally based on, gosh, what was it called? Susan Aitken that made it. Well, we might could get it to work, but takes a while. So let's keep looking. Still taking a little bit. While it's doing that, I'm going to pull up for you. Okay, here we go. All right, so down here is the number of observations and the relative time period. So for this relative time period here of, this would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So that's 16. So if you want to see what that's talking about, okay, so I need a time till variable. Tab time till. This is the right here. Those negative. It might be doing this. Maybe that's actually, but it's got 500, 750, 1,000. Why does it go back down? Well, that's confusing. I don't really know. Thought that was what that was doing. All right, but look, it's getting an event study. All right. But what about the ATT? All right, so it's all buried inside here. So if we type in return list, It's in here. There it is. Okay. And here's each of the individual, like it actually calculated all of these. How many is that? 36. 36. Okay, so we got all of those. I don't know what all this stuff is. This is the cross validation, but I got 36 of those, so you could aggregate them however you wanted to. Yeah, let's get the bootstrap, or let's see what this is. So we're gonna do right here. See what this is. Oops. $68.33. 68.33. So how do I get the bootstrap? How did we do it? So in our paper, let me just check one thing. So I think you can get standard error, mat list. Ah, there we go. Mat list. So you get the ATT 1.16 standard error, and you get confidence intervals from it. So I should put that in there. Mat list. Okay. So it's handling differential timing. And in this case, actually, the parallel trends is satisfying unconfoundedness. All right. Now what I want to do is I want to show you how we used it in a paper. All right. I just want to double check that I have the newest. Yep, I think that's it. So the newest one I have, I was kind of hoping to get some updated stuff. So I will show you our when it's time. I don't have it here, but I'll show you this paper. So this paper, yeah, 2024. So it started in a long time ago, 2017, maybe. Let's see. Looks like 2016. So it took a while. I think our first submission was probably always starts to keep 2017. And if you look at it originally, the very first paper, okay, if you Google it, I don't think matrix completion was in there. And not only that, there's nothing in there about the diff and diff stuff. There's nothing in there about the Bacon Goodman, Allen, or Callaway, Santana, or Sun and Abraham, or any of that, because this paper was submitted in 2017, and that was before the diff and diff stuff. So this was like a really tense period. So gets rejected at QJ, story of my life, and then I think we probably sent it to AER. Okay, I don't have a thing there. JPE, nothing. All right, so I think we go then restud, nothing. And then we go to management science. Do I have, here we go. Now, I don't know when this year is, 2019. All right, so let's see. Bacon, whoop, bacon, still nothing. Matrix, I start using matrix completion. So I do a robustness check of the treatment effect using matrix completion. I must have just read it. And so we start using matrix completion, but we're using matrix completion before we even learned about the biases of two-way fixed effects. Okay, so I don't even think, yeah, we don't know. So it gets rejected at management science. Let's go to EJ. Yeah, management science. AJ applied, rejected, JHR. What happens here? Bacon. Still in the original submission, 2019, February 2019, I had not read any of the new robust diff and diff stuff yet. I was trying to get the mixed, I had a contract coming with the mixtape with Yale that summer, and I believe I had written the year before, the summer before, I had written the mixtape and posted it on the internet. And so we submit this paper to the Journal of Human Resources and we get an R&R. We get an R&R, but we've got matrix completion in here. Okay, we got matrix completion, but we don't have any mention of the bias of two-way fixed effects. So then we resubmit. I wonder if I say it here. So I think I might, yeah. So then what happens is we start realizing in the response letter, that there is this literature that, like, because I'd had December 2020, I had already submitted the mixtape, so I knew that the diff and diff stuff on two-way fixed effects was biased. So we start changing it like they didn't ask us to do it, but we started changing it. And all we really started changing was we started really just building into the paper that the two-way fixed effect, it wasn't just that matrix completion was a robustness, it might be necessary. That's how we started doing it. So I'll walk you through how we did this paper. But I only have a deck going back to January 2020. So I bet I don't have. Okay, so I do. I start doing the two-way fixed effects. So I wanted to show you how we did this paper. Okay, so this was a paper about Craigslist, and it had an erotic services section. So for those that don't know much about me, from 2007 until this paper, which was published in 2024, I pretty much, my whole career was on studying sex work. And this was my last paper on it. So my work with Todd Kendall had been focused on how the internet had reorganized sex markets and reduced street markets. I had papers on that. And also we speculated that it had created systems of governance and coordination through the websites having these rating websites. We had found one and scraped it. The sex workers claimed that these new websites had made them safer, made it easier to coordinate with clients. This is the first paper to study it. I'm not going to spend a ton of time on this paper, but I just want to show you how we did it. So first, what we did was we estimated two-way fixed effects using the erotic services, which I'll show you in a second what that is. And we found that female homicides fell 0.013 to 0.023 per 100,000. Doesn't seem like a big number, but the baseline of female homicides kind of low in the first place. So it came to be around 10%, upwards of 17. This is the matrix completion number. Matrix completion gave us a bigger number. Two-way fixed effects is typically biased downward with differential timing, so that was a bigger number. We sort of hypothesized these mechanisms, but what I'm sort of trying to say here is that as you do these synthetic control methods, you can't really lose sight of the larger bodies of evidence that you need to really put together. The larger body of evidence that you need to get together is you need to show bite that the program that you're studying has some impact on the market, that you're trying some impact before you start getting into outcomes. And then you show a lot of falsifications, and then you show event studies as best you can. All right. So we don't really know exactly why we find this. Could be that street workers are moving indoors. Could be that trust was being created by Craigslist. Could be some sort of weird disruption that we can't identify. Could be some substitution of violence patterns. Sex work historically is very dangerous. It's the highest homicide rate for a workplace, if you want to call it that. Female sex workers' homicide rates historically were 204 per 100,000. Second most common homicide rate for females was the liquor store employee of 4 per 100,000. Homicide rate, another study. These are always kind of difficult to compare, but one study found that sex workers were killed at a rate that was 13 times higher than the general population. They're the targeted groups of serial killers. 65% of serial murders are female. 78% of female victims of serial killers were sex workers, according to that study. 35% of all sex worker homicides were by serial killers. We're not saying that this is disrupting serial killers, but it's like another anecdote that this is a group of people that are very, very vulnerable. All right. 3 types of sex worker websites. Prior to Trump passing something called FOSTA and SESTA, there were these websites that were allowed to function. There were these advertising websites, there were review boards, and then there were verification websites. I was able to get these two. I was not able to get anything from the verification website. So we scraped Craigslist erotic services. I have gotten Eros before for a project, but Craigslist erotic services is the one we're going to focus on. And we're going to use the erotic review data to go with it. All right, we're going to use these 2 data sets to go with it. So here's Craigslist. Craigslist was, at the time I wrote this paper, the 15th most popular website in the United States. It offered cheap advertising, better matching, more business, lower search costs. With Facebook Marketplace, I don't know how it's doing anymore. But anyway, it was a low-cost advertising section. This thing called the erotic services was a section on the front page. And you could think of it as like, the Village Voice, the alternative newspaper, had also a section that was called adult services. And that would be where escorts and massage parlors would advertise. It was sort of a open secret that it was sex work. Craigslist at some point, was not trying to compete necessarily with newspapers. At some point, it became clear that they were going to be doing that. And they began to put in more newspaper advertising as opposed to what it was in the beginning, which was in the beginning, it was this guy named Craig Newmark, and it was his list. It was just his list of stuff like that he would post every day in the Bay Area. They posted erotic services. Instantly, it gets captured by illegal sex work. It's openly being used to advertise by sex workers to clients, prices, photographs, all this kind of stuff, and the types of activities. And from '02 to '09, it ran, but then it was voluntarily shut down in 2010 due to harassment. That's kind of provocative language. When I wrote the paper, yeah, harassment's not, harassment probably is the right term, but they were constantly being like pressured by attorney generals and activists to shut this down. Eventually they do. They shut it down in 2010, and then the Village Voice owns something called Backpage. Backpage steps in and they absorb the traffic. We were collecting data at the time before Craigslist shut down. Backpage basically did not do anything. They had an erotic services section. Craigslist initially kind of responds to pressure from the Attorney General to start an adult services section where they're going to more aggressively police it. But the moment they get rid of erotic services and replace it with adult services, it's like Backpage is born. Backpage just kind of then begins to move up. And when Craigslist shuts down, this announcement here is made that they're closing, Backpage just goes up. So there's like a replacement that does happen, but I can't really study Backpage because Backpage is just this like seamless transition from Craigslist. So we're going to instead study Craigslist and see what the effect was of Craigslist. So we frame Craigslist as a clearinghouse. I don't know if that's the right way to think about it, but we were struggling to kind of figure out how do we communicate to economists what we mean in this. So it's a matching market that matches. Well, no, it is a matching market, but there is no matching function. It's search, and clients will search on there. The sex workers will advertise. And what it did in our argument was it reduced the search costs and it reduced the advertising costs because it was originally free. Eventually, in response to the attorney generals, they raised it to $5, but it was originally free. And it increases we believed that what it was doing was thickening the markets, making the matching more efficient, because the clients could sort of figure out who was in an area, and rather than drive around or things like that, they could sort of search, they could contact these people, they could interact with them before. And my claim, although I don't know this, is that the sex workers might, through this email correspondence, have more time to sort of figure out a little bit more information about the client, which might allow them to, match better. All this is speculative. There's no way to know, not without data from sex workers. And could you really get into that kind of question? And, when you would, I've only kind of qualitatively interviewed sex workers over the phone or online, and they've not always gone really well. So I don't really know exactly, how believable this is. I will just show you what we find. But we speculate, that we think that this is probably a reasonable preference ordering of a sex worker. That a sex worker there are basically four types of clients. There's a client who shows up on time and he pays her and he is not violent. There's a client who maybe doesn't show up. She doesn't get any money. He shows up intoxicated. He's unprofessional in some way. He haggles over the price, but he's not violent. She would prefer to match with this guy over this guy. Third person is a police officer. She would prefer to match with either of these people to a police officer. And then the fourth person is a violent male. And probably, it goes without saying, I think probably that's a reasonable ranking. Okay. The problem is they all look exactly the same because there is like no obvious difference between any of them. So street workers probably could not differentiate the type very well. Maybe it was harder for everybody to do it. Our argument is that the sex worker, by having email interactions through this Craigslist platform, they don't have to make these split-second decisions. They're not even out in public. They're just waiting at their computer or on their phone. Back then, it would have been pre-smartphone, so they would have had a telephone. So they would have their email. They could email them, try to learn a little information. They could call their client at work. They could do background checks. Many of these individuals were very sophisticated, doing a lot of things. Not everybody, though, was equally sophisticated. We did a survey of people, though, and about 65% of the sex workers that we interviewed did require things like this: references. They would use white lists, they would use black lists, they would use verification websites. So there was like some kind of attempt to screen. And if a client could pass any of these screens, well, it's not perfect, but a Bayesian updater might be able to say, you know, I'm more likely they can Bayesian update. Now, the Bayesian updating could be wrong, but these are definitely, some of these are more difficult to overcome for a violent male than others. So, you know, if he or she requires a reference, well, that's gonna be hard for a violent male and a police officer to supply. And there was study. Here's a book written by a woman named Bass. So having the ability to advertise online allows sex workers to more carefully screen potential customers and work indoors. Research shows that when sex workers can't advertise online and screen clients, they are often forced onto the street, where it is more difficult to screen out violent clients and negotiate safe sex. They're more likely to have to depend on pimps to find customers for them. But that's qualitative. It's based on qualitative interviews. So there's this staggered rollout. So this is like Craigslist 1.0. This is like New York City. There was a personal section. And that's it. Here's a services section. Resumes, freelance, small biz. These numbers represent how many advertisements they had on that day. And I got this by going through the Wayback Machine. So you can go through the Wayback Machine and you can search. So we searched every police jurisdiction that had an associated city. We searched the entire history for all of the cities in the data and found when this happened. And this is this New York again? This is Dallas-Fort Worth. Dallas-Fort Worth on this date, whenever it is, suddenly has expanded its services from 3 to 14. And the 14 services are computer, automotive, creative, household, erotic, labor, event, skilled trade, financial, real estate. So here's all the cities in our database, because we're using the supplemental homicide reports. And you can see in 1995, this is all the cities. And in 1995, there is no Craigslist erotic services. In 03, Houston, I believe that's Houston. Houston has one, and then the Bay Area. 04, 05, 06, 09. Nice little data visualization. Highly recommend use maps when you can to illustrate the rollout. So here's the data. We use the Wayback Machine to get the dates of when Craigslist erotic services was adopted. We get this erotic review data, which is available by month. Erotic review is client reviews of sex workers. We get the supplemental homicide reports to get murders of sex workers. And then we get the summary uniform crime reports part 1. I believe this was for the falsifications. The final version has rapes, but reported rapes, but originally we only were studying murder. So this is going to be our falsifications. So the Wayback Machine is just a robot with a camera taking pictures of websites every day. We went through hundreds of cities month by month. First time ERSS appears in a screenshot, is considered the treatment date for that city. All right. Another paper did this very same thing. It was published in the American Economic Review back in December of 2002, but they did it for Facebook when Facebook first appeared at a college. So there's a lot you can learn from the Wayback Machine to get a lot of information. But when we did this, when we used this Wayback Machine, this was the idea that I came up with, and I had never seen anybody do it. But we knew we were doing Craigslist, and we didn't think it was a big. I didn't think it was a big deal per se. But now, as time passed, when I saw that paper go into the AER, I thought maybe that was pretty interesting to people. So the Erotic Review is a review website. It's different than the advertising. It's not advertising. It's like Yelp, and I've published a lot with it. So we scraped this data on April 2017. There were 1.4 million reviews, hundreds of thousands of unique providers or sex workers. We used the total female homicide rate because the data on sex worker homicides is not available by city panel. The reason is sex worker deaths are undercounted in the FBI due to some weird reporting rules. Here's the reporting rules. Monthly reporting schedule for participating agencies requires agencies to report homicides in the month they are discovered, even if that is not the month in which they occurred, or if the social context of the homicide is not yet known. Sex worker homicides go undetected for weeks, months, or years. So the supplemental homicide procedures have a built-in bias toward under-ascertainment of many sex worker homicide. It's not ideal to just work with the female murders. It's going to add noise to our estimates because sex worker homicide is just a small part of it. But there was no other way to use it with this design. So when you do a study like this, you want to first show bite. Here I call it first stage, right? This is the Erotic Review front page of it. You know, showing pictures like this to people is usually helpful. Here was this interesting thing. This is T.S. Christine, and you have to fill this information out, okay, to be on the Erotic Review. And it's filled out by the client. And look what the client put. He put her Craigslist email. Well, the Craigslist email is an anonymous email. It's a scrambled email that's not even going to be there for another week or so. But that's all he had, so he put it. So we just looked at, we did a recentering by the treatment date, and we just wanted to know, you know, when do we suddenly start seeing Craigslist emails? Now, they're not very large, okay? They're not very large, but Craigslist emails start showing up at a different website when Craigslist opens in that city about 10 months later. So then we start looking at things like, you know, independent versus working for an escort agency. These are not diff and diffs. They're not really even interrupted time series. They're not RD and time. They're just simply showing that, like, you know, interestingly, you've got this downward trend. This is the share of people that are independent, and it had been gradually declining till Craigslist enters, and then several months later, it reverses. And then we looked at, you know, did you work for an agency? Over time, what happened was the website starts getting really used by agencies. Everybody's moving on to the website. But then when Craigslist comes on, it just kind of plummets. So these are kind of ends up being two of the things we study. So I'm going to skip all of our two-way fixed effects stuff. I'm going to skip that and go to our this. First, I tried to figure out, you know, how believable was the parallel trends assumption. Okay, it's untestable, but what I did to try to test it was I literally wrote Craig Newmark and I asked him, hey, when did y'all and why did you open Erotic Services? And here's what he said. He had been following me on Twitter for some reason. So I wrote him. I said, and he said, Scott, thanks. I haven't been a Craigslist spokesman nor in management since 2000, have had no part in decision making. However, you're asking a question involving sophisticated marketing, economic analysis, and business development. And as a matter of public record, Craigslist doesn't share that. So nobody knows why Craigslist enters. The only thing I can say is that Craigslist, where did I say this? Craigslist does not tell a city they're coming. They do zero advertising. So the one thing you do know is that prior to treatment, every city is untreated. There is no anticipation even possible because nobody knows. So we do these standard event studies. And this is what we find using two-way fixed effects. We sort of find these things here. Leads are jointly significant with P of 0.9, lags 0.01, right? Heterogeneous treatment effects across time will bias two-way fixed effects. So we do some falsifications. We look at murders of women by partners. We look at murders of males. We look at manslaughters. And these are our, this is the 10-month, this is the first 10 months after Craigslist opens, and this is the long run. And we never find anything for Craigslist murders by your partners. We don't find any effect on men, although the standard errors are a little big. Here it's like more precise zeros, but here the standard errors are big. And for manslaughters, it's a little bit more precise. This is my favorite one of the falsifications. They are not statistically significant, but the standard error is big. But these others are a little better. Poisson is bigger, but this is, there you go. That's what we have for our falsification. So what do? We argue for, because, we were doing matrix completion prior to the diff and diff stuff. We were aware of Bacon's paper before I was aware, really, before I even understood Callaway-Santana. So we knew that because everybody eventually gets a Craigslist, we had a potential problem. The later to the early had a pretty large weight on it. Now, the diff and diff associated with it wasn't very big, but there was a lot of weight being placed on those bad controls. So we chose matrix completion, which we know will identify it. So we sort of explain it. We had to limit it to panel units that had less than 90% panel units treated. Otherwise, it wouldn't converge. So we had to drop the units treated at the end of the panel, just like I was saying to you. Here's the unknown matrix that we are estimating. Regularization parameter, like we said, originally we were using GSynth and it was working. The standard errors came from bootstrapping, and we found that negative 0.23 off of a baseline of, we were using as our baseline 0.13. So it's actually like kind of big. We do all kinds of stuff in it. And that's it. Then we do some mechanisms. Why does it happen? And so, we find that, like, when Craigslist enters, there's some strange things that start to happen on the website. When Craigslist shows up, the word street, we start looking at these things. What happens? The word street starts to disappear from reviews, falls 15%. Prices go down, and the looks and the performance scores decline. And so this is like our suggestive evidence that we think it might be that Craigslist is bringing street-oriented people indoors by allowing them to match. And So we also see the word repeat go up, repeat customer go up about 2 to 3%, and then these in calls grow about 9%. People have a lot of opinions about what in calls mean. Some people are like, oh, in calls mean that it's in calls are more dangerous than out calls. No, in calls are safer than out calls, and they're going up. But I'm not positive that that's true. Which is, that's what we find. So there's that street goes down, repeat goes up. So that's us using matrix completion in a paper. That's how we used it in a paper. We were mainly using it as an alternative to difference in differences, specifically alternative to two-way fixed effects. But as we showed here, we can with you can estimate. I mean, this is where things would more things probably are needed to really be done. You can use Callaway and Santana also. So we said, all right, 68.33 off this data set using matrix completion. What if I use Callaway and Santana, which is a diff and diff estimator? Let's see what it finds. It's also bootstrapping. Okay, so it runs it. Let's do that simple average. 68.34. You can do the groups, you can do an event study, Look how similar. That's what we found with the matrix completion, right? So, what's not really clear yet, what's not really clear to anybody, I don't think, is what is the precise situation where matrix completion with nuclear norm regularization is able to be unbiased and yet, and not is able to be unbiased, but the standard diff and diffs are not. And and because it's like under this unconfoundedness assumption, you get parallel trends. So I was trying to play around with a lot of stuff. Like I'll show you here. So here I'll show you a biased. What I did was a simulation, and I have a biased diff and diff where I do not have parallel trends. Okay. And I'm going to estimate matrix completion with nuclear norm regularization. Now, if I don't have parallel trends, in my case, the control group and the treatment group have differential trends. Well, if they have differential trends, then that does not satisfy unconfoundedness, because unconfoundedness says conditional on the covariates, the two groups are comparable. So I'm going to show it to you. So I'm going to do it here. Let's watch this run. And we may have to take a break while this runs. So what we'll do is while this runs in the background, we'll take a 15-minute break and we'll compare. What are we going to compare? We're going to compare a diff and diff two-way fixed effects with matrix completion. So we'll look at that when we get back, but we will not satisfy parallel trends, and we'll see how it performs. All right, so we'll give us 15 minutes. So 33, 38. Come back at 30. Come back at 40. Come back at 40. See you in a minute. I believe finished with the bootstrap. Um, let's see what's going on real quick. It's still spinning. So we may have to, oops, we may have to look at this when we get back. All right, so, all right, let's look at what it's making here. So it's 41. Just making another one. All right, so let's see what it's doing. All right. Because that does not look biased. It looks unbiased. So I'm wanting to see here, where does it make that image? It's making it here. Here. Probably I did quietly. I got these things. I really want to see what it is. We may have to like take a lunch break and then come back. But let's look through what this code is doing. All right. 40 states. 40 states. Got an experimental group. And the experimental group is the first 20 states. You have 50 cities per state, 10 years. All right. And then I assign the year. Okay, it's going to be it's going to be the simple, what this is going to be is this one. Single treated period. Single treated period. So I'm going to have one treatment period. It's going to be the year after 2015. All right, here we go. So I'm going to have an experimental state and a non-experimental state. I'm going to have a group of married women. Baseline here, $40,000 is just a number I'm going to have. And then if you're in the experimental state, you're going to be making $80,000. And if you're in the non-experimental state, you're going to make $40,000 at baseline. Then I am going to create, so if it's like 2,000, annual wage growth. Oh, okay. Yeah. So it starts at 2000, then it goes up. So if it's a year after 2000, your baseline will be 40,000 or 80,000. If it's a year later, it'll double. Okay. I'm going to have an error term here. I'm going to have an error term. On average, 0. Your Y0 is going to be, basically a little noisy. So your Y0 is going to kind of move around a little bit. It's going to be this number plus some error. All right, Y1 is going to have an average treatment on the treated of negative 5,000. Okay. And so pre-treatment. Yeah. All right. So it's going to be, I don't know why that says negative 5,000. I think that's supposed to be 1,000. And I think that this is actually unbiased. I don't know why it's called biased diff and diff. I must have saved over it. All right, well, this is gonna be another this is gonna be another diff and diff. So this one's gonna be the non-differential timing. And I'm gonna have a treatment effect. Post-treatment, it's a constant of negative $1,000. So we're going to have a diff and diff. We're going to do matrix completion. And then we're going to calculate the ATT. So the matrix completion Yeah, so this is not a bias. So I need to make a bias diff and diff. I must have that hidden somewhere else. I do have a bias diff and diff for matrix completion, and it also remains biased. But the issue is that it automatically does not satisfy unconfoundedness. So I've still not quite found a data generating process that works with matrix completion that doesn't work with diff and diff. But this is halfway done. All right, so it's going to have to look at this later, but you can see at least the event studies. I'm getting approximately close. I'm almost getting, I've got such large error. See, the error term is so big, but I'm getting around a negative 1,000. So matrix completion is working with the diff and diff situations, just like it said. It's working with the single treated period block structure. I haven't yet used it towards the synthetic control. That was probably dumb to start with the one that's taken so long. Wish I'd have turned, I thought by doing quietly, I would turn off the figure, but it's making the figures. So, so we know we're finding unbiasedness with this. We have built into it though, unconfoundedness. We know we have done it with differential timing, and we're fine, you know, at least we looked at its implementation with differential timing in a simulation that was giving us an unbiased estimate. We looked at an application in a real paper. The only thing we have not done is this synthetic control. So I will, when we get back from lunch, we'll kind of break and we'll look at that. So I'm gonna stop there. Parting comments. Review this again. This model can be used for differential timing. It can be used for simple 2x2s. It can be used for synthetic control. We haven't seen much in terms of contrasting it with the robust diff and diff estimators like Borsak et al., Callaway, Santana, or any of the others. It's going to be coming down to these parallel trends assumptions versus this factor model, and communicating those improvements that you gain with synthetic control as you move away from the simplest comparative case study and moving away from diff and diff. That might be a challenge that you're going to have to think carefully about as to whether or not in this matrix completion, you know, can you explain the identifying assumptions easily? Okay. So you need to choose the estimator based on the problem you're studying and the assumptions. You have to justify it. No one else can. And you do so by appealing to the assumptions and whether or not the data fits it. But we're seeing, I guess, in general, we're seeing that, you know, matrix completion with nuclear norm regularization is identifying the same parameter, average treated on the treated. And so far, anyway, we've seen a couple of data generating processes where it is giving us the same result. So what we're going to do now is I'll open it up to any questions that anybody might have. We have 10 minutes before lunch about anything that you might want to ask about matrix completion that we've seen, or from anything that we've seen. Does anybody have anything they want to ask? All right, Eduardo. Yes, I certainly can. I'll get the new version from JHR. think I can download this. No. If everybody gets treated, you can't do it. Matrix completion will attempt to, but you're not you in Stata it will attempt to, but it's not a it is not. So if all of the units are eventually treated, then there's nothing to wait. Okay, because remember what you're doing is you're weighting units that have Y zeros. So if they're treated, they can no longer function as the counterfactual. It's a good question. Well, what we're going to see, it's not obvious to me, which it's not obvious at all. It's not obvious actually that it is. You're going to use augmented synthetic control is not depending on an unconfoundedness assumption. I really don't know. I really don't know. I don't know if Kyle knows. But the assumptions here are this unconfoundedness assumption, and in augmented synthetic control, it's these factor models. So it's not entirely clear. I mean, part of what Synth is turning out to be is that Synth will work with factor model assumptions, and it'll also work with I think AR autoregressive models. So, I don't exactly know when I would do it because, Eduardo, what we're going to see in a moment, when we look at augmented synthetic control with staggered adoption, it's used for those very purposes. So I'm not entirely clear, exactly what would be what it would be. I mean, I haven't seen in any of these like papers that have been coming out from Susan Athey and Embens, they will sometimes have these horse races in the papers. They'll have their estimator, like synthetic diff and diff, run against other papers. So like I wonder if here they do the smoky one. Okay. So what do they compare it with? They're going to compare it with these phrases come in. VT. Two elastic net. I don't know what the VT is standing for. All right, but it's definitely not. One's called HR, one's called elastic, both elastic net ones. All right. So here's two elastic net ones. Here's Abity. Here's matrix completion. So they don't play it against augmented. And what they're looking for is the root mean squared error associated with it. And diff and diff means two-way fixed effects, simultaneous adoption, staggered adoption. All right. Now they're not showing the bias in here. They're just showing the root mean squared error. But where's theirs? Here. So it usually has, so this is the number of time periods divided by T0. So post-treatment divided by the total. Or maybe it's pre-treatment divided by the total. But Yeah, it does better than two-way fixed effects with the longer pretreatment. That doesn't answer your question about augmented. So if I open up augmented, let's see what they did. Nothing. So the only thing they cite Athene, but it's just the only thing they're doing is citing related work. So it's a little, these are all such new papers that there's not as much clarity around how to compare these things. Um, can it deal with missing data? Well, there is matrix completion. There are methods for dealing with missing data, multiple imputation methods for dealing with missing data. Matrix completion is not designed for missingness like in a traditional sense. It's really designed for the missingness is coming from the treatment assignment because it's really only going to handle outcomes and you know they like the outcomes go from y0 they go from y0 to missing. There are methods for dealing with the missing data, but it won't be this one. I don't know how it would perform to use those kinds of patterns if that's like a general kind of missingness thing, but but it's not designed for that. Yeah, yeah, it'll handle any of that. Um, it'll handle any of that because that's just going to change, that's just going to change the number and the interpretation of the causal parameter will be in rates versus levels. But if that is the potential outcome, then, that'll be what it'll handle. Yeah, that's fine. As long as you can write out, I mean, the whole thing that you have to remember, Ronald, is just can you write out, y0, y0. This is the outcome for a unit if not treated. Y1 outcome for the same unit if treated. Y0, the matrix is of Y0s, and some of them are missing because they switched to Y1. So if your unit of observation, well, yeah, I mean, if your parameter is like is the average treatment of the treated is, the change in the rate, I don't see why it would matter. So it should be fine. As long as as long as you can think of that Y0, Y1 outcomes in that way, then it's not going to matter. You forecast Y0 from both the horizontal regression and the vertical. So it's doing both of them. It's going to project, I mean, it's basically that nuclear norm regularization is using patterns in both up and down, left and right. So it's forecasting Y0 and it's using units that are comparable in the pre-treat. It's doing synthetic control and it's doing forecasting at the same time. Forecasting for yourself and synthetic control types of regressions at the same time. Okay. All right, I'm going to stop there. By the time we get back, hopefully it'll be finished. And what we're going to do when we get back is we'll work on, I'd like to do the augmented synthetic control, I think, first, and then conclude with synthetic difference and differences. But we have an hour lunch break, so we'll come back 2 minutes on the hour. All right, so y'all take a break, and we'll see you soon. Play and all right, so I've updated the slides. If you wouldn't mind pulling real quick, I kind of changed the outline a little bit. I didn't like the order. I decided I wanted to go from augmented synth to the augmented synth with rollout. Matrix completion comes second, then synthetic diff, because these are the same authors, and then also these are the same authors. So it's a little out of order, but I just didn't like it. So all right, let's go over here and look at this. All right, so I've got this simple diff and diff situation, parallel trends. I run through it. I've got two cities, and both groups of cities are going to get, both groups of cities are going to get, well, there's going to be a group of cities that's going to get treated, and then a group of cities that won't get treated. So we're going to generate here Y0 is going to be equal to the baseline plus 1,000 a year times however many years it's been. So notice everybody's growing by 1,000 a year. So we've got parallel trends. Then I generate this error. It's got large variance, and I'm going to replace Y0 to equal all of this plus that right there. Then I'm going to have the potential outcome Y1 equal Y0, unless it's the experimental group and it's after 2015, or it's 2015 or after. And then there'll be a negative treatment effect, constant treatment effect. So we already looked at differential timing. Okay, we already looked at differential timing. Now we're looking at that simple, situation with a single treated unit, single treated period, and seeing how that compares. All right, we got this treatment indicator here, treatment effects. Okay, so we've got this ATT. I'll show you what the ATT is in just a second. Then we're going to assign treatment. So the only treatment's going to be post-treatment period for the experimental group. That's when it's going to switch from Y0 to Y1. And we're going to estimate a diff and diff, regress earnings onto diff and diff specification, keep that coefficient, call it diff and diff. Do the matrix completion, which took forever, took about an hour. That was horrible. And we're going to save that there. All right. And I did that 100 times, and I have a new seed each time. So I seeded it, went through seed 1 to 100. We're going to get an ATT, a diff and diff, and a matrix completion, right? Saved it as results.dta. I wonder if that means it's right here. Not sure where it went. Anyway, it uses it. All right, I got this bias term, so I'm just going to show you the bias of diff and diff and show you the bias of matrix completion. So if we just summarize it, you can see here the ATT is a negative 1,000, and diff and diff is getting a negative 1,009,313. Matrix completion getting the exact same thing. So we're seeing the performance of matrix completion is performing exactly in the same situations well as diff and diff. The bias inconsequentially smaller. It's a little bit, they're both a little bit biased, but you know, you'd have to do this a lot of different ways to see, but matrix completion is slightly less biased. I'm not positive why that is, but you can see right here, what we've got is just matrix completion, and we also have the diff and diff. So again, we're sort of seeing a situation where matrix completion is generally able to perform, you know, exactly in the under that scenario too. And I could do a synthetic control. I guess I could do a synthetic control real quick, and maybe we just code it up and just see how it does, because I've never done it before. Okay, and we just go over here to this. All right, we're going to look at BM prison. All right, treat's got to be we need a treat variable. All right, so we're going to get gen treat equals 0, replace treat equal 1 if state FIP equal 48 and year greater than equal to 1993. All right, so we got a treat variable, got a state FIP. All right, we're going to run it. I'm not running this that many times. I'm going to run it 10 times. That's 100. All right, let's see what this does. I am not positive how this will run. I don't have any covariates. I do have a lot of covariates I can put in there. I'm not positive how to do so this I've never done before, but look at that. So there it goes. You're getting a bootstrap confidence interval. I only did it 10 times, but it's pretty interesting. I've never run this before, but we're finding pretty similar to what we did before. We're not getting the gap, you know, from it. Well, no, this is the gap. This is that gap, but we're not getting the randomization inference. All right, I'm definitely going to save that. So what I don't know, what I'm not positive is, that's pretty interesting. Well, well, we can see here what we've got with the let me find it. Unconfoundedness, synthetic control. We were getting with unconfoundedness, we were getting these parallel trends fits that. Parallel trends is, you know, unconfoundedness includes parallel trends. Parallel trends does not require unconfoundedness, but it includes it. So we're getting that with our this right here. Let me show you. So we're getting it with single treated unit there. That's our synthetic control that we just did. Single treated period. That was our simple diff and diff. Okay, that was our simple diff and diff where everything happened in 1 year. It was getting that. And differential timing. So far, that was pretty fascinating. So far, you know, we saw 3 sort of situations where matrix completion is operating in a very similar way to both diff and diff scenarios and matrix completion and synthetic control, which is what they claim is that it encompasses all of them. More analysis probably would be good just to kind of dig into that. But you can at least see that their argument that it's all three of them, that you can sort of see that it's with those data generating processes, it was unbiased. I think trying to move away from the diff and diff, the parallel trends versions of unconfoundedness would probably be a really good next step. But what I'm going to do now is we're going to go to this multiple treated units and staggered. So I'm going to now go into this augmented synth with staggered rollout. So imagine we hadn't done matrix completion. We were kind of going into this already. You know, synth was originally designed for a single treated unit, no extrapolation, non-negative weights that sum to 1. That was like the original use of it. And they said, again, that you need a long pretreatment time series and you need, it was for 1 unit and the weights were non-negative. And so you needed a perfect fit. So the first thing we did was we said, all right, well, what if you can't get a perfect fit? What do? There's a bias adjustment method based on Abity and Embens 2011. You could use that one. When you use that bias adjustment, it'll reweight the donor pool units slightly negatively. Some will get positive, some will get negative. Nothing, you won't have the same sparsity. You won't have that anymore, but you'll have something else, some of which are negative. But it was still 1 unit. It was still 1 treated unit. So this new paper, they kind of wrote these 2 papers at the exact same time. And this new paper focuses on multiple units with differential timing. All right. It doesn't have to just be differential timing, but it allows for multiple units and it allows for multiple units in differential timing. And so you could think actually now of this method and that matrix completion method. You could think of both of them as maybe belonging inside that differential timing literature. And I'm not saying that you go do all of these. This is part of the headaches, I think, of this current world we're living in, which is we now have many different methods and it's not obvious exactly, what's going to make a person choose one over another, right? Because all of the assumptions are a little bit abstract and all of the techniques have the same diagnostics. And those diagnostics, for the most part, are the event studies. So it's getting a little bit challenging, okay, to do anything with. But these are all kind of in this causal panel literature. It's causal panel literature. In fact, I should probably Embed's causal panel. We should probably post this. This is this came out last month. I cannot spell. Argonskis. Just go ahead and put that in there. Okay, so you can peruse this, but one of the oddest things about this paper that you're going to be sort of think is weird is this is intentional. This is how Embens wanted cites to be. That's a citation. Never in my life seen that. So that's Abity. Never in my life seen that. Somebody said it was a mistake. They wrote Embens, and he said, no, I like it. I want them to do that at I want to do that for all the econometric articles. I don't know. But so if you're interested in a lot of this, okay, you could read this really closely. And we get into all of this same material um here. So they don't cover it in all of it. You can see they don't really do a ton on augmented synth. But if you're having a lot of questions after this is over, and you're like, well, what do I need to start choosing between? Probably this is your Bible. This is your Bible. This is what you want to study really closely. All right. Because a lot of these things are starting to overlap with each other. And that's just where the world has gone. That's where the world has gone. For decades, you did with causal panel, most people, there were some things that some people did, but a lot of people just did fixed effects. And that has turned out, once this new diff and diff literature came out, and we realized that the original two-way fixed effects estimator was biased with differential timing and heterogeneous treatment effects, specifically dynamics. I mean, it is kind of odd the way this happened. These people, Callaway Santana, Andrew Goodman Bacon, Son and Abraham, the Chase Martin and DeHopeful, Borsak, they were all graduate students or assistant professors. And in my reading of it, they were not really in communication with each other. They wrote some of these things in graduate school. And why do I bring that up? Because we went from a single method, two-way fixed effects, that was being used over and over for policy analysis, to about 6 papers on diff and diff. And they all use parallel trends. They're all very similar to each other. Don't use an already treated group as a control. They have different ways of doing it. There's like a weighting approach, which is the Callaway Santana, Son and Abraham, the Chase Martin. And then there's an imputation approach, which is Borsak et al., Jeff Wooldridge, John Gardner. And so you've kind of got these like already 6 diff and diff methods for when you have differential timing, all of which are using parallel trends. And if you kind of go back to Causal Inference II, and you just look at, for instance, this paper that came out a couple of years ago, here, this paper on mental health and social media, that's a diff and diff where they use the Wayback Machine and find exactly when colleges got Facebook. Let me show you what they find, what they do, and this is becoming pretty standard. They show this picture, right? They show this picture, all of which are, and this isn't even all of them, Borsak, Son and Abraham, Callaway Santana, two-way fixed effects to Chase Martin. They don't show Gardner. They don't show Moondlock by Jeff Wooldridge, okay? And they definitely don't show any of the synth ones, Matrix Completion, any of them. And so, like, where am I going with this? It's kind of like a Pandora's box has been opened up a little bit because, all of these papers basically were invented simultaneously by graduate students who lacked each other's social network. They weren't really presenting it and learning from each other. There's tons of redundancies in them, especially in the originals. The working papers, tons of redundancies, lots of theorems and proofs that would carry over. All right. Well, as this is my conjecture, I think the world now, one of the things that happens is everybody goes, well, which one of these do I use? Which one of these do I use? And the answer is, it's like a lot of subtle details, a lot of very, very subtle details beyond what I can cover right now because I covered it in the diff and diff workshop, but a lot of subtle details will make the decisions for you. But the point is, I think a lot of people now go, oh, diff and diff is a lot more complicated than I thought it was, because I thought diff and diff was a regression. So it's a lot more complicated. Well, now as these synthetic control methods are coming out, and they are no longer just being used for single treated units, they're now being used for differential timing and getting used for simultaneous treatments and these other things like general kind of unconfoundedness situations. It really, really starts to make you wonder where this is all going, because there's just absolutely no, I mean, it's almost like in graduate school when we would learn um, so many different maximum likelihood methods or so many different IV methods. And you would and it's almost like we've had it really easy for a long time, where you would just kind of have this one thing you did. It was some version of a regression. And so it's a little bit, I find it to be, I mean, I hope that, I'm not bumming you out, but I find it to be it's a lot. Hold on. So I just saw I say, can we use an unbalanced panel or matrix completion used only in counterfactual imputation? I think matrix complete, that's a good question. I believe matrix completion will balance. That's a good question, Todd. I thought, I cannot remember. I know the answer, but I can't remember. We can look at the break. I'll make a note to just double check on MCNN using imbalanced panels. One of the things, I will say this, one of the things probably that is making some of these diff and diffs a little bit more attractive is that took an hour for that matrix completion to run, So that's one thing, is that was an awfully long time. If you think about it, that was an awfully long time. So that's one argument, that you might keep in your mind. But I do think that this clearly merits a lot more careful study. Okay. All right. So let's look now. So, but this is the thing. The standard approach in the diff and diff, the standard approach when you have differential timing is diff and diff event studies, but those all require parallel trends. And so when parallel trends is not viable, then your estimate is equal to the average treatment on the treated plus this non-parallel trends bias term. I mean, it's that simple, but that non-parallel trends bias term can be anything. It could flip the sign even. So synthetic control methods have been updated. And, this team here, Ben, Michael, Feller, and Rothstein, they weren't the first. I think it was matrix completion that was the first one, but they were working squarely inside that synth framework. I mean, so was matrix completion. So here's what synth with staggered adoption is, though. Synth with staggered adoption is basically a way of trying to manage doing multiple synthetic controls and then trying to find a way to combine them. So let's say that you're wanting to really find the effect of a concealed carry gun law on crime. You don't want to know what it is for California. You don't want to know what it is for Texas. You really want to know the average effect, right? If that's what you're doing and you decide to do these synthetic controls because you do not believe parallel trends holds, all right? So you're going to do this synthetic control. You're going to be trying to, if you want to know the overall effect, not what's just the average effect in one state, you're trying to kind of aggregate into a single parameter, right? The goal of this paper is to do that. That's the point of this paper. The point of this paper, it's not just the staggering part. It's like trying to aggregate. How will we go about aggregating something as unusual as a synthetic control, which is already kind of got like event study pieces to it. How do we aggregate it? And they're going to propose, they're going to introduce that there are these two biases in this thing that they're doing. There's these two biases in this thing that they're doing, and they're going to talk about a heuristic or like a tool that you can use to sort of balance. You can use this tool to kind of balance between two biases. And we've been talking about biases. So it's kind of carrying forward the bias from the last one. It's the covariate bias. It's the pre-treatment fit bias. And you're going to have some way of trying to choose a certain parameter that will like get you as close as possible to either a bias that's like very small for the average or a bias that's very small for the individual states. Okay. And they're going to have as their working example a teacher union collective bargaining law and a teacher salary study. So Jesse Rothstein is a labor economist. He studies education. He's at UC Berkeley. And so that's probably part of it is bringing that in. But we could do anything with this. I don't have another I don't have another application. So we're going to look just at their vignette for how they do it. But you could do it. You could do it for, I just don't have, I wanted to do it when I had a longer pre-treatment time series, but you could do it. You know, there's actually some cool stuff you could do. So you could do it with any kind of, any kind of differential timing scenario. So let's look at this. So estimating effects under staggered adoption means the same thing as differential timing. With staggered adoption, you have multiple units getting treated over time, and the common approaches can fail. Diff and diff requires parallel trends, and synthetic control is designed for single treated units, and it's going to be poor fit on average. So the partially pooled synthetic control, they could have easily called this the partially pooled synthetic control. They decided to call it well, actually the paper that I have here is just called synthetic controls with staggered adoption. Let me just double check what this thing is called, because that is the first time I've noticed that. Eli, hey Michael. This is Eli Ben Michael. He's in the stats department at Carnegie Mellon. Let's see. They just keep going. This is Sophie's son. She has son and Abraham. You got 2 new papers. Oh, just called staggered controls with staggered adoption. Synthetic controls with staggered adoption. So I am about to change it. I thought it was called this. Hold on. Right. Sorry. I can't help it. Because if I don't do it now, I won't do it. Give me 1 second. Paper was published though in Journal of the Royal Statistical Society. And then this one was published in JASA, which was in that special issue that had matrix completion in it. I wish I could get this. I'll get it and I'll put it up there. I think that'll be fine, but just double check. Apologies. Sorry. I just want to make sure that I get this right. Yeah, because it's still saying it wrong. You always have to run it twice. Unless you're on overleaf, in which case it's automatic. And there we go. All right. All right, perfect. All right. So core idea, balance the imperfect balances. So common approaches can fail. They could have easily called it partially pooled. They didn't. They just call it synthetic control with staggered adoption, but they're going to propose a particular kind of synthetic control. It's one that is pooling together all the individual synthetic controls. All right. That's the approach, but there's a way that you can do it that has been done it historically, and they're going to talk about that historic way of doing it and say don't do it like that. All right, so this is going to be the study they're going to do. They're going to study a teacher union collective bargaining law and the effect it had on teacher salaries. So every now and then a lot of our analysis is just going to be from this. Okay, so from 1960 to 1985, you had collective bargaining events that happened with the teachers' unions. And this is like a long literature. It goes back apparently to Carolyn Hawksby, 1996. What's Lovingham's first name? Well, and then 2009, Lovingham. So I don't know this literature. I'm not in education, but there's been 33 states that have granted collective bargaining rights to teachers. Long literature, impact. Hawksby finds increased spending, 12%. This person found nothing. Using the ever treated states. Not sure what that means. So traditionally, though, they all did two-way fixed effects, but we know that that is biased with heterogeneous treatment effects, specifically dynamic treatment effects and differential timing. So they're going to reanalyze all the states and the synth models, and we're going to review it using their code. Okay, so here's like the standard event study in economics. This right here is a relative event time indicators. This right here is an indicator, like creates dummies. This is a dummy maker. And these are year minus treatment date. And this is like years after treatment date. These are going to be the pre-treatment leads, and these are going to be the post-treatment. These are going to be the post-treatment estimated average treatment on the treated. So key assumption is parallel trends with this model, as well as constant treatment effects. So there were two approaches before this. One was like John Donahue. Let me show you this John Donahue paper. I saved it for you guys here. So John Donahue reanalyzed data on concealed carry laws. These were laws that would let you carry a weapon in public, but nobody knew. And there was a famous paper, or famous like hypothesis, more guns, less crime. And it was proposed by John Lott and David Mustard. This was ironically the paper that I read right after I graduated college. There were two papers I read right after I graduated college that made me decide to be an economist. One was Gary Becker's Nobel Prize speech, and the other was Lott and Mustard's 1997 article that evaluated a bunch of states that passed these concealed carry laws and looking at the effect that it had on crime. They found large negative effects. They found when these states passed these laws, crime fell. They were using the county level data. Every time I try to replicate this using the state level data, you don't even find what they found. But anyway, Mustard was at the University of Georgia. And so and then that county level data that he had collected, he gave it to some people at Emory University who also reads those are the only two schools I applied to because I was so enamored with Becker and this like quantitative approach. So, this has all been kind of fascinating for me. So they claim that the right to carry laws decrease violent crime. He goes back and essentially redoes. Let me give you an example. He redoes all of the states using synthetic control. Let me give you an example. Here we go. Estimating the impact using synthetic control. Synth has become very popular. It's a promising new statistical approach. And while most synth papers focus on a single treatment in a single geographic region, we're going to do 33 adoptions occurring over 3 decades throughout the country. For each adopting state, we will find a weighted average of the other states' synthetic control designed to serve as a good counterfactual for the impact of the law. By comparing what actually happened to crime with the synthetic control, we generate estimates of the causal impact of RTC laws on crime, at least for those states. And then he goes through and he kind of says it. All right. And so here we go. He illustrates it in 2 states. Figure 5 shows the synthetic control graph for violent crime in Texas, 77 to 06. The solid black line shows the actual pattern of violent crime. Vertical line indicates when it went into effect. He lists the weights. So he finds this positive effect of when they adopted it. And, I think you could, well, we don't know the other states, so we can't really look at the pre-trends to see if the other states would satisfy parallel trends. He seems to have found a set of states that are doing something. There's imperfect fit right there. So then he does another one, Pennsylvania. Now that's pretty incredible. That's remarkable. So I don't know what this 89 is. So he's got to figure out now, what do I do with these things? And so he's got all of these synthetic control estimates, and he just kind of takes averages of them. All right. So this is like what he calls the separate synthetic control method. Estimate separate synth models for each state, the past concealed carry laws. It's obviously can only work if you can find good, evidence, if you can find good fit for each one. But it can lead to poor fit for the average, leading to bias when the average treatment effect is the target parameter. So if you're only wanting to know the effect for Montana, you might be okay. But if you're wanting to know the effect for all the states, you might not be okay. Because as you start kind of adding these together, the little bit of bias in all of them could just cause the overall average to just look abysmal. Okay. So an alternative approach, and they don't actually give a citation for this, so I'm not positive who did this. But another one could be to minimize the average itself. So rather than go after separate synths and combine them, just do one. Just do one synthetic control where it is literally the average of all the states. Okay. And you can achieve nearly perfect fit doing it this way for the average treated unit. But The thing is, I mean, you can kind of sense a little bit of the tension that if you like if you get okay or pretty good fit on the individuals, and the average, like if all the error, just kind of imagine if like every one of them, the error is like always in the same direction, then like when you aggregate it, the aggregate one's going to really blow up that error. Here, it's like if you could somehow manage to get it to look good of your like complete average, like from the start, it's probably going to be the case that the state level fits are going to be bad. So their proposal is to do both of them. It's to do both of them and to sort of minimize a weighted average of how bad each of them are. And you're going to have like it's not a tuning parameter, but you're going to have this particular random variable that you can use. It goes like a scale between 0 and 1, and it forms a frontier, and you can kind of pick where you want to be on that frontier. So we want to balance the average of these factor loadings. If you balance the individual units, can cause large imbalance on average if the errors are not canceling out. Now, if all the errors are canceling out, then you could have like slightly biased states, but like, sometimes it's over and sometimes it's under. So on average, the average one looks great. That's probably not going to happen. But, balancing the average outcome, though, and I'll show what that looks like, may not actually lead to you getting those factor loadings correctly modeled. And so you might be, it won't be like overfitting on the noise, but it would be kind of masking the fact that it's a severely imbalanced synthetic control. You just have kind of masked it. So they're going to try to trade these off of one another. So this is the John Donahue. Estimate individual synthetic controls and then average them. So look, here's the averaging right here, and here's individual synthetic controls. Notice our weights have two subscripts now. Subscript J is referring to each of the separate scents, and subscript I is the donor pool. Okay. So what you're doing is you're getting estimates of the treatment effects. And, it's like he does it here. You're getting just like an average of 14.3 by averaging over all of them. Versus, that's average separate scent, versus average the treated unit by pooling together everything. So alternatively, we can think of it as a cent estimate, 1 cent. So this would have been 33 cents. Like he did 33 of these. Okay. 33 synthetic controls, and then you average them. You're only going to do 1 synthetic control here. Here. And what you're going to do is you're going to go 1 over J. J is the number of that. J would be all 33 of these. 1 over J. Y in every period, okay, averaged. All right. So it would be like, in 1995, that'd be like 425. And in 1995, that would be like 650. So 425 plus 650, 425 plus 650 divided by 253, 7.5. And you would do that. You would literally do it for everybody. Okay. You'd still have to have enough units untreated for the time periods, but that's what you would be doing. And then you would estimate the average here. You would be getting these weights and, averaging over all of the weighted synthetic controls to go with that. So here they are. Okay. Here they are separate, 33 individual synthetic controls averaged, 1 synthetic control based on the average. Okay. Average Y, and then averaging over the pooled. Okay. So they say, all right, which do you want to do? Now, what they're basically saying is like, let's go back to the optimization problem. Remember, the optimization problem for synthetic control was minimize the squared. We don't have the V here, but like minimize the squared the sum of the squared discrepancy gap. Okay. Versus minimize the sum of all the X's minus the weighted sum of all the X's squared. So they're like, both of them are matching discrepancy, but they're slightly different, and it's different targets. It's different targets. So the weight here that minimizes this one and the weight here that minimizes this one's probably going to be different. It's probably going to be different. So you're going to get different solutions. All right. So here's like the separate synthetic control method. They're going to do Ohio on this mandatory collective bargaining law. All right. We're going to do Ohio. And looks pretty good. You do got that bad thing right there. These are in that, like these always happen. You've got something bad right there that happens. But looks like there's a positive increase in spending for Ohio. But when you do California, it's a big negative. And notice how they recentered it. They do in this recentering. All right. Big negative effect. Then they do Kansas. Kansas, you know, positive. And then they do New York, and just, you know, this is again, the problem. They can't do everybody. I mean, in some ways, this is going to be really bad. You know, diff and diffs don't have these problems with these positively weighted controls. Okay. So diff and diff doesn't have these issues with these outliers. They're just all based on who's treated at that time period, who's not treated at that time period. Okay. So here's the full spaghetti plot. So, you know, doesn't show us it, I don't think. Aggregating. So he's going to aggregate. But yeah, he's not showing us everything. Okay, but here they like overlaid everything, all the states that did this. All right, this is the full set, and some of them aren't very good. Some of them aren't very good. So this is not the placebo analysis. This isn't the placebo analysis. This is all the states. And it's really hard to decipher it. So they kind of like average over all of them. And so this right here is the average of all the synthetic controls. So if we go back a couple, it's averaging 33 synthetic controls. That's the average over J. And, you know, it's the YJ at a point in time. And that's what that purple line was. And so doesn't look very good. Doesn't look very good. Even though it looks great for some of them, doesn't look very good. The pre-treatment doesn't look good either. So by contrast, if we balance the pooled treatment units, you can get perfect fit. But when you get this perfect fit, if you optimize to on the pooled imbalance, the pooled balance will be good and the state balance will get worse. And this is kind of a feature of this aggregation, which is that you really you cannot, like, to go in one direction is gonna give up something in the other direction. To get to get more balance on the individual states, because you sort of separately do them, when you aggregate it, it can get bad, and vice versa. So optimize the pooled imbalance. Pooled balance is better. State balance is worse. It's bad for state estimates. So balancing on the covariates doesn't mean that you're going to end up balancing on the Y zeros. So, so this is their proposal. This is their proposal. I see you typing, Ronald, so I'm just going to get this ready. So their proposal is a weighted average of the pooled model and the state balance, and then this penalty term. And the thing that we're really going to focus on is this V. All right, is this V. And the returns to this are going to show a highly, it's going to be highly convex, setting V just a little below a certain number, setting it a little below 1. All right, we'll get a big improvement on this one, even though you're just barely doing it. You set it to like 0.99. You've barely changed the pooled balance, but you can get big improvements in state balance. It's a good question. I don't know the answer to that, Ronald. I don't know the answer to that. I don't think so. At least on these have been, you know, they've all been recentered. So the ordering, if you did it chronologically, well, what these are doing is they're proposing an aggregation that puts everything into relative event time. So that's what they're trying to do. They're trying to put everything into relative event time because the average treatment on the treated, well, the average treatment effect is it's going to be in, like, for some states it might be 1980 to 1985, and in other states it might be, 1984 to 1985. So they have to try to find a way to, what they're trying to do is they're trying to just basically turn this back into the standard differential timing scenario where everything's in these relative event time. So I don't think that the chronological part, so why couldn't they do the chronological part? I'm not sure. There's nothing that would stop you from doing it. There's something that would stop you from doing it. Yeah. It's just that if you did that, it wouldn't really be a single cent. It would like be you'd have like treatment effects over here, here, here. They'd be everywhere. So it might not be interpretable. That's an interesting thought. Let's take a 15-minute break real quick. Since I know that this is a dense paper, let's take a 15-minute break and we'll be right back. All right. Let's look at this sucker. So, instead of minimizing either, you're going to be minimizing a weighted average. Okay. And you're going to use this as your goal. This is the thing you're going to be sort of kind of moving between. All right. So V is the hyperparameter. It's a fraction, can go from 0 to 1. It's not a fraction. It can go to 0 or 1. If it's at 0, if it's a 0, then you're doing what Donahue is doing. And if it's a 1, you're doing this thing I've never seen anybody do. So it governs the relative importance of the two objectives. Higher values of V correspond to more weight on the pooled fit. Higher values of V are going to be the pooled balance. So higher values of V correspond to more weight on the pooled fit. Lower values of V put more weight on the John Donahue approach. So it's important, so you're basically trying to figure out, well, which V are you going to pick? And they don't really say anything like an optimal V. They're going to put it in your hands to do, but they have a heuristic that they use that they sort of suggest. But it's important to control. They're both important. it's important to try to so this one is really important. Getting that right is really important for the overall ATT, and getting this one right is really important for the individual ATT. So in general, we want both. So the following figure that I'm about to show you is what they call the balance possibility frontier. The y-axis here is the amount of imbalance in the wait, is that right? Y-axis is the pooled imbalance. Yeah, pooled imbalance, right? It's the pooled imbalance. So when the pooled imbalance, oh, got it, right. So separate, yeah. So typically, yeah. So this is when it's high over here, okay? It's like when it's high over there, it's got, oh, okay, yeah. So this would be the bias of the separate. So that would be like average state level imbalance. So that would be like over here. I'm confusing a little bit because of this, but we'll get to that. So when it's really high here, you're getting this imbalance here. And when it's high pooled, which they do not, that's the problem, is it's not showing that. When it's high pooled imbalance up here, the separate one might be better, is going to be better. There's this trade-off between them. It's this convex, this balance possibility frontier is actually a trade-off between both of them. So the curve that we're about to show, you trace it out. You trace out a curve by just allowing this to go from 0 to 1. Right, when that's 0, from going from 0, which is going to be all state balance, to 1, which is going to be all pooled balance, you end up with these two extremes. Okay. And there it is. All right. So that's what it's going to look like. And this is all measuring the imbalance associated with the two the two different like aggregations. Okay. So you can pick like to be right there, a V of 0.5, you would say, all right, I'm gonna be somewhere in the middle. And that would be like, you'd have a certain amount of pooled imbalance there and a certain amount of the average state level imbalance. Okay. Or you could choose to do that. And a V of 0.99, all right, a V of 0.99 has just barely reduced its, like, that's a V of 1. All right, that's a V of 1. So just going from 1 to 0.99 has a huge return on reducing that average state level balance. That's why they say it's highly convex, because you can get a whole lot of a reduction in imbalance on one margin, and you really didn't pay for it. It's like it didn't really cost a whole lot to do it. So I'll just kind of show you. So that's what it cost you to go from all the way from 0.15 when you set that to a 1, when you set V to 0. Okay, you set V to 0, you're entirely V to 0. No, that would be V to 1. Pooled balance. What's the V again? Which one is which? Keep forgetting. It's this fact that these words are not, and I keep forgetting. When V is 0, it's the separate. Okay, V is 0 is the separate, and there. Okay, it's all there. It's all pooled balance. All right. So you get big gains. So even going from 1 to 0.99, when you're trying to figure out a way to, I mean, again, just kind of stepping back for a minute, you're trying to get, I mean, imagine you're going to the president and you're trying to tell him this is the overall effect of this like mandatory collective bargaining law. Okay. And he's wanting to know. And he knows that the only way you could get to that answer was by evaluating all of these individual states. And your job is to come somehow average them. And we go back to what, Donahue did, and he just kind of he took an average, but then he also tries to aggregate them, somewhere in here. He tries to do an aggregate itself. So even going from 1 to 0.9 cuts that unit level imbalance by 30%. So that would be like 0.15 to 0.1. So that's 5, right? He goes from 0.15 to 0.1 out of 0.15. So that's, 0.5 out of 0.15. It's about 33% reduction in state level imbalance. All right. So it cut it just by barely tweaking it with almost no change in the pooled fit. So just like the pooled fit looks almost identical, but all of a sudden your state fits are getting better. In many cases, it's going to be possible to trade off. It's going to be possible to do that kind of thing. Trade off a small increase, just a little bit of increase in pooled imbalance for these large reductions in how bad your state level fit looks. So that would probably be a better estimator of the overall ATT when you think about it, because your pooled imbalance is virtually identical, but your state levels look better. So it's almost like a free lunch. You did pay for it, but you didn't pay much for it. But then there is a point where you start having to really pay for it. So to go from this one to this one, right? To go from 0.1 to 0.85, that one, you did have a little bit. So all of these things, you're kind of like imagining just like a dial moving it back and forth, just trying to figure out how you want to present this. But the key idea is that if the separate, so they have so the balance frontier, it's a tool that you use to try and trace out the trade-offs between these two pooled and unit level fits. And then you just choose whichever you want. Okay. But they do provide a heuristic. I was going to write down the actual equation for it, but it was a little bit harder I thought it might be better just to do it pooled fit. So they use a simple heuristic. I actually can pull it up. In our application, we use a simple heuristic. In our application, we use a simple heuristic to set V based on the pooled fit of the separate SCM. And just so you know, again, pooled fit of the separate SCM. That's the pooled fit of the separate SCM. Okay. That's the pooled fit of the separate SCM. All right. So they use it. They say they use that. All right. So we set V to be the ratio of the pooled fit to the average unit level fit. So that's what they choose. They choose V hat, and then this is where it was kind of hard to do it. So we find through simulation that this heuristic results in weights that significantly reduce both the estimation error for the average treatment on the treated relative to these separate synthetic control models and the estimation error of the unit level effects relative to the pooled. So in the teacher bargaining, their heuristic gave them a 0.44. So if you're asking yourself, what would you do? That's one thing you could do. Or you could ignore it altogether. So here they compare these things that they did, the separate, pooled, and what theirs is, the partially pooled. And theirs is, somewhere between them. Okay. And then they do their state level root mean squared error kind of calculations. And here you have in the unit level here, the accuracy of the prediction. And in the partially pooled, all right, partially pooled, you've got, fairly good prediction here. You do have some outliers that are not very good. Then they're going to have this augmented part of it. They're going to augment the staggered adoption. They're going to estimate an outcome model, just like we did. So this is the part of it where they used to call it the augmented synthetic control with staggered adoption. This is them introducing the staggered adoption. So they're going to have an outcome model. They're going to estimate the partially pooled set. They're going to use this outcome model to adjust this for imbalance, the bias correction. They're going to be applying the bias correction that they worked out in the previous paper, or they'll use this other method, this doubly robust method. But we didn't really talk about this, so we're just going to say the bias adjustment. So they also look at this special case where they're going to allow for, if you've got, you still have imbalance, they're going to allow for a level shift. But this is their augmented synthetic control. All right. And this is they're gonna do a weighted diff and diff. So here you have their augmented synthetic control, Y in the post minus Y in the pre minus a weighted synthetic control in the post and pre. They're going to have a weighted event study. And the weighted event study is going to shift this balance possibility frontier left. Here's the diff and diff. And here's this partially pooled synthetic control with intercept. You can still make improvements. You can still make improvements over this pure thing if you allow for an intercept. The intercept, what the intercept is doing again is I'm trying to estimate this messy, and this synthetic control messy, he's such an outlier, I can't do it. But if I put an intercept in, then I can do it. He's just like, it's the best players are looking like him, and I'm going to have a level shift to push him up there. Okay. And when you do that, you can get both of them to improve. It's just that this right here is, that's not within the framework of that original Abity paper. This is in the framework of this Duchenko and Embens paper. Okay. So the weighted event studies, they're going to shift that balance plus possibility frontier even further inward, giving you less imbalance on both of them. And then when they construct this comparison group, the event study estimate of the effect on spending ends up being statistically insignificant. These confidence intervals, they are large, so they're not, the point estimates are negative, but the confidence intervals are large. So if you remember, Carroll and Hawksby had found positive effects, but they're finding negative effects of the mandatory collective bargaining law on school spending. And then they're finding negative effects on the teacher salaries too. So synthetic control, very useful for difficult problems in which parallel trends is not plausible. Large T, perfect balance. You just need to, with a large T and perfect balance, you're good to go with that original synthetic control estimator. You can use synthetic control to get approximately unbiased treatment effects, as we saw in the original. Perfect balance, though, is very hard to get. Perfect balance typically is harder to get the more volatile the time series is by nature, you know. So the papers that Abity has written using synthetic control where it looks really good, those are things that almost are just fixed at a stock level and just really small changes in the flow. Smoking, GDP. You know, GDP is very smooth except for in recessions. So you'd have to kind of be a little careful of a recession. But other than that, you know, they typically work really well. But with something like stock markets, you know, stock returns, it's going to be highly volatile. A lot of these things become really difficult to get good fits, in which case, you know, to study those kinds of things is going to have to enter into this world of trying to deal with imperfect fit and then aggregating it. So augment this. Caesar, I have literally never seen anyone do this paper. You know, this is the thing. It just came out 2021. Let's see how many times it's been cited. $161 times. These all kind of are. All right, what's this one? Bardic's using it. Well, okay, yeah, it's Jesse Rothstein. So Jesse Rothstein used it. So it'd be kind of interesting to go through all these, or Jesse Rothstein cited it. A lot of these actually are method papers. I wonder what this one did. This is in the AER. Populism at the country level is at an all-time high. You know what? Let's look. I don't have the subscription, so let's see. What do they do? They call it the doppelganger average. That's interesting. All right, so what are they doing in this paper? Okay, this is a great paper. I definitely need to incorporate this in. So this is about populism is at the country level is an all-time high. 25% of nations currently governed by populists. How do economies perform under populist leaders? We build a new long-run cross-country database, study the macro history of populism, identify 51 populist presidents and prime ministers from 1900 to 2020, show that the economic cost of populism is high. After 15 years, GDP per capita, wow, 10% lower compared to a plausible non-populist counterfactual. So they've got multiple shocks. You can see here, they've got multiple shocks, differential timing. So they're going to bring it up here. We use recent advances in Centh for multiple treated units with partly staggered adoption. I probably do need to teach the Abity-Lahore, but I have not yet. Estimate partially pooled synthetic control model following them, which combines a weighted average of the separate synthetic controls for each treated unit with a pooled synthetic control estimation for the average treated unit. Okay. Let's get to some results. There's a lot in here. I was thinking, looks like they're doing a lot of different things. So they're doing prediction interval methods, multiple treated units. Here we go. Abity point out that in the case of the multiple treated units, a unique weighting matrix for each treated unit may not exist. They develop a penalized version. All right. Here we go. So it looks like they're doing a lot, Caesar. This is a good, we're going to put this in the thing here. Okay. So what do? They proposed the partially pooled, aimed at minimizing the imbalances. They calculate a weighted average of separate cents determined for each treated unit, pooled synthetic control. Notice how everything's in relative event time. We use their method to show partially pooled estimates in figure 11. That's it. They don't really go into a lot of detail. So it looks like the way it looks like they're going about it is a kind of robustness, right? That's what it seems like to me. But this paper literally just got published. 2023. It just got published 4 months ago. So I encourage us to read this and kind of see how they did it, but it doesn't look like they did a whole lot. It doesn't look like they did a whole lot. They didn't really say a whole lot. You know, why do they not? I wonder why they didn't do Callaway Santana. Huh. No difference in differences. So they do not do difference in differences, and they do not appear to be saying the word difference in differences. All right, so I need to that I did not know there was this new AER. So that's interesting. So they do these time placebos too. Look, they set it all back 5 years. But all of these are aggregating. All of these are aggregating. So pretty interesting. Augmented scent is allowing us to salvage the method using an outcome model, differential timing, averaging them all together. You know, I remember Susan Athey gave a presentation at the continuing education class on causal inference and machine learning with Hito Imbens. And she said that when she showed synthetic control to Microsoft back in 2010, because she was the chief economist at Microsoft, when she showed them the pictures, they just got stunned. And I wonder a little bit if that's not something that should stick in our minds a little bit when you're thinking about choosing between these methods. You know, the principles of, I'm rambling, if I can ramble for a minute. The principles of matching are, when they're combined with time, people really do find those things to be incredibly compelling. when they're not combined with time, and it's just like matching at a point in time, there's not as many like things you can do to convince someone it's a good match that you've matched on unobservables, right? Because you can only match on observables. The thing about synthetic control is if you can create a match that tracks it over time, it's got a better argument that you've kind of matched on those unobservables. That's that factor model idea. Unobserved heterogeneity is inside the determination of the outcome. You've got the observed and the unobserved part, and only the good matches on the observed and unobserved would produce the same time path. Now, here's the thing. He's looking at real GDP. And so Ronald, you study countries. You might be the candidate for doing this kind of thing, Ronald, because GDP is just so smooth and it just goes up, a lot of the time. The kinds of work that I do, it's been a huge pain. So like I'll show you real quick another paper of mine that does it. This was a paper where we were studying methamphetamine precursors, the kind of the key inputs used to produce D-methamphetamine. And there's two of them. There's ephedrine and there's pseudoephedrine, Sudafed. And over about a 15-year period of time, the American government's trying to regulate access to pseudoephedrine, first at a wholesale level, and then increasingly at like retail level that was really impacting the consumer. And Mississippi and Oregon passed the most restrictive laws. And those laws were blocking your ability to buy Sudafed, the cold medication, without a doctor's prescription. In 2005, everybody had to purchase behind the counter, but in Mississippi, you needed a doctor's note. So we got data on the location from the DEA on the location of every illicit lab that produced methamphetamine. And we did synthetic control. And this is the United States. Okay, this is Mississippi. And then we did synthetic control. So it does look a lot better. Okay, I mean, actually, that does look good. But it's nothing like GDP, when you just kind of compare here how GDP, I mean, it's like the root mean squared error on these fits is basically zero. But over here, it's not zero. You get imperfect fit all the time. Okay. And, when they pass this law, there's this large reduction in any labs that are in operation. And here you find the effect. Okay. And you could sort of average this whole thing to get an average tree on the treated. Really worked out really well. We find this, large effect, but we ultimately found no effect on prices. And so we kind of argued that it doesn't appear to be affecting the market. It's just affecting these local. I mean, I'm from Mississippi, so it's like it's just kind of affecting the local guys making it, but it's not affecting any kind of importing into the state. So all that to say, here's my point. All that to say, and I can put that paper in real quick. I can put that in. All that to say, these really clean ones are just heaven on earth, because the fits are just, there's all the donor pools are so easy to pick from, they're so easy to pick from. And so they do placebos that we haven't really talked about. They're finding fake dates. They go -5 fake dates, and then they basically fit their model here, predict right there, find nothing. That's a time placebo that's highly recommended. So I guess to answer your question, Caesar, is that paper's in the AER. It's country level data. I don't know all the pieces about what to think of. Country level data seems like these macro models might have been a little bit more interested and open to it. But yeah, that's probably a good paper for me to really dive into. So looks like it's getting some traction. 161 sites since it was published in 20, whenever that was. So it is picking up. It is picking up. Kind of rambled a little bit. Glad you asked that question, though. I wouldn't have found that paper. So partially pooled scent is an extension that we haven't really considered with differential timing. Here we have an advancement into this differential timing, okay, that we did, that we still want the long pre-treatment, though. We still want the long pre-treatment. And I think this long pre-treatment part can be one of the things that is causing you to choose diff and diffs over synth. The long pre-treatment, when you get a long pre-treatment here, and the longer it is, the more likely it is that you're not fitting on the noise. Yeah, you totally can. You totally can. I would say Taha, though I think it's at the daily level, that it's going to be pretty volatile. That's my overall hunch. But yes, you can. You totally can. I mean, you can use any kind of time, and probably during COVID would have been a potential application, maybe, especially for mandates, shut and because you do have some. Well, during COVID, the amount of daily data was ridiculous. Yeah, yeah. Although you're matching on the seasonal units, the seasonality is kind of being captured in that factor model. But yeah, these are all things I've not thought about before. Yeah. Let's dig into their code. All right, let's dig into their code for a second. So I was playing around with it, and that's the AugSynth prison. I've got their knitted file. I pulled all of it out, but I thought we would look at the knitted a little bit. And all this is doing is recreating everything they did. So let me show you where it is. I tried to, and real quick, I'm just going to fit this. Okay, so we have some new stuff. All right, so we can open this up here, open file, and it is, all right, it's under Texas. We need to clean this up. Me and Kyle need to clean this up a little bit, but it's under Texas. Oh, sorry, my bad. Documents, Causal Inference 3, labs, it's under Texas. I got to clean this up. R, AugSynth. We're going to do AugSynth staggered. Okay. And at the moment, I don't think there's a Stata version. All right. So I'm just going to go ahead and start knitting this. Here, I'll get this. So here we go. Is it going to make an HTML? What's it going to make? Yeah, it's going to make an HTML. So it's doing it. Okay. All right, let's see what they put together here. All right. So this data is this is their collective bargaining agreement, public sector unions. They got the data from this paper. All right. And it looks like we need this library, Dippler, AugSynth, and you need to install it using that. Data's here. Okay. And several important variables, year, state. So it's a state panel. Year collective bargaining required. This is the year that the state adopted mandatory collective bargaining. Okay. And here's the outcome. Log pure per pupil expenditures in constant $2010. So multi-synth is the name of it. And to run it, we need to include a treatment status column that indicates which state is treated in a given year. So it's not coming with that data. So they're going to create that, and they're going to restrict it to years 59 to 97, where they have yearly measurements of expenditures. They're going to drop DC and Wisconsin. They must probably be missing data or something. So here we go. They're going to assign treatment here, okay, filter it there, and then you're going to get treated if year is after CBR required, and then that'll be your a column called CBR. So CBR is our treatment variable. CBR is our treatment variable. All right, so partially pooled synthetic control model with an intercept. All right, so to fit the partially pooled synthetic controls, we need to give multi-synth a formula of the form outcome treatment, point it to the unit and time variables, and choose the level of partial pooling new. See, I was calling it V. I actually did not realize from the paper it was a new. So I need to change that. But I was doing V. Okay. So setting the new equal to 0, remember, does the separate synthetic control for each treated unit. Setting it to 1 fits the pooled. We don't set new. Multi-synth will choose a heuristic value based on how well separate synthetic controls balance the overall average. By default, it includes an intercept shift along with the weights. We can exclude that intercept by setting that to F. So are they going to do that? No, they're not going to do that. So we can also set the number of pre-treatment time period lags that we want to balance with this argument, and the number of post-treatment time periods leads we want to estimate with the leads. They didn't do that either. By default, it sets it to the number that's in the data. Okay, so here we go. With a choice of new 0.5, what is that? So 0.5, remember, is here, there. You know, just kind of arbitrarily on that. We don't actually see the balance possibility frontier yet, but we're going to do it here. 0.5, called that P pool sin. And then we're going to do P pool sin $ new. So here we go. Do it once with the choice of new. That would be that one. And then do it with the default. They don't really say, you know, what it is. I mean, the use of the intercept, Eduardo, is actually in order to address any imperfect fit. It's kind of like the intercept allows you to go after some of these outliers, is what it does. It allows you to kind of go after some of these outliers, because just think of the intercept as like just pushing it up or pulling it down. So, you know, insofar as you believe that it'll have better fit, less, you know, imbalance in doing it. And I'm just thinking out loud. I would think if you're doing multiple treated units, you're probably going to have to do something like that. Because if you're doing multiple treated units, some of them are probably going to have to be outliers. Otherwise, you wouldn't be able. So I think that probably they're going to want you to do it. I mean, this team, I think, really is I heard through the grapevine, Abity was not crazy about these papers because both of them paired together really do say we're just going to ignore this we're going to ignore this convex hull stuff completely. And so they kind of just embrace the idea of get the bias down any way that you can get it. So allowing the intercepts is, I think, is always going to allow it to be less biased. And so they're gonna allow for it. So here you got, if you want to see the new here that was produced, it's a 0.26. It's gonna be up here, right? So when it's 0, it's all on the state balance. Okay. So summary function will compute the treatment effects and the standard errors in the confidence intervals for all the treated units, as well as the average using a bootstrap. Takes a while. So we're going to change the significant level associated with it by setting the alpha. By default, it's going to be 0.5. So here we have our object. People send some. Where'd it go? Oh, that's what it's making. People send right here. It's the last one that was run with its own chosen endogenous new value. And we get it in here. So it's summarized, it gets it in here. Then you report the level of global and individual balance as well as the ATT. So here you go. You report it. All right, here's your average ATT, negative 0.11. Remind me again what the measurement is. Negative 0.11. This is spending. Logs. Okay, logs. So it's log reductions, negative 0.11. Yeah, so it's like in here. So it's about a 1.1% reduction in pupil spending, if that's the outcome. That's pupil spending. Is that what this was? Pupil spending, yeah. So it's automatically doing the intercept. Yeah, it's not significant, but it's negative. That's consistent with these big standard errors. Here we have the global imbalance, scaled imbalance, percent improvement from you. So here he reports how big the improvement was, 98.1 on the global, and then the individual, we get this improvement too. So here's our lags. Now we get our event studies. Any of these significant? No. So none of these are significant, but here's our treatment. Here's our post-treatment, all 10 of them. So that goes to about a negative 0.05. I don't know. That still seems a little different. But anyway, there it is being reported. This no pooled send sum ATT, it's a data frame, contains all the point estimates. Oh, well then because that's a particular new value that was the new value that was chosen. So we get average effects here. Contains all the point estimates at each of the time periods. You can visualize it. Display both the pre-treatment balance and the estimated treatment effects. So some of these, there really are big, the effects are everywhere is the problem. We can hone in on the average effects by plotting P-pool, send some, just remind myself where that was from. P-pool, send some here, which came from the people sent here, right? So you did this is where it's all starting. We're doing the multi-cent on this with an intercept, because without the intercept, it's without anything. If you don't put this in, then it'll automatically do put an intercept in. And here we're getting that new. So it's that. And this contains all of this. Now we want to get the average. Oh, there it is right there. Right? Think. Not positive. That's it. I think that's something else. So here we get the average. Huge confidence intervals. My friend Andrew Baker told me these confidence intervals, every time he uses them, they're massive. So we can collapse. So now we're going to collapse into time cohorts. These are like Callaway Santana group time, average treat on the treated. So you're going to go by time cohort, true, print it, compare the effects to the overall, plot it. So we get our average. There's that average there that we got. And here's all the cohorts. Rather than do it by state, do it by groups that adopted at the same time. But again, getting the average. You can sort of see the value of doing this, I think. Which is if you've got a lot of heterogeneity and you're wanting to summarize it into a single parameter, you know, you're going to have to figure out how you're going to do it. And then you can put in auxiliary covariates. Where does that go? Here. Multicent. You'd put the vertical line and then you list them. Do it again. And that's it. Okay. So a good homework assignment. I'm trying to think, do I have a really good differential timing? I don't have a great differential timing inside of our I do have one here. It's in Causal Inference 2 under labs. It's the Ching and Hoekstra. Ching and Hoekstra will Ching and Hoekstra will only has 10 years of data though. So that's not the best one to do. But you could, I'll start looking around and get a better, there is the Klein and Moretti, but I think the Klein and Moretti is just a 2x2. Yeah. So that would be a good exercise. A good exercise might be to take could always take a minimum wage paper. Could always do Singa's, you know, Dubé, Zipperer, that QJE paper. That would be interesting. But that's a good homework assignment. That's a good homework assignment to try. Actually, no, I do have one. Let me just real quick while I got you on the line. I just gave this assignment. Let's look at this job displacement data. No, shoot. All right, I'll look around. I need to put one in there. I need to put a differential timing project in here. All right, let's take a 15-minute break. And what we're going to do when we get back is we're going to do this synthetic diff and diff. All right. It's been a long day. Let's take a 15-minute break. We'll come back at 3:20, 3:21, and rest right now. We'll be right back. Okay. I'm having fun though. So I'll see you in a second. Okay. This is a lot. This feels like a lot that we have covered. I appreciate you guys hanging in there. I just lost it. Hold on. And we're gonna do synthetic diff and diff. And you know, the thing is now that we've it would have been really nice, I think, to have gone in that order. I think going from here to here would have like been really cool because now then we'd go to here. And I don't know if I have a great plan for, I mean, I will say that when I step back, my way of teaching this is to tell like a narrative a bit. It's like tell a story of these papers. I can't help it. That's kind of how I teach, is always like, where's this flow going? As opposed to do it in this situation, is do it for this, do it for that. And I know that can be a little frustrating. So I don't really know exactly, what to say about these two. Um, I'm not really sure, how to, I still don't quite have it in my brain, these two differences. Seasonal effects using the staggered adoption. The the thing about the staggered adoption, okay, is the thing about the staggered adoption is imagine, well, okay, imagine you're doing the original synthetic control, one state, right? Where's the seasonality effects? Right. Well, let's look. Seasonality effects. Where is it? It's the longest way ever. Here we go. All right. You got a factor model producing the potential outcome, and the seasonality effects are right there. Probably. They're the year fixed effects, right? It's like there's a time element that affects all the units the same. And then there is this the lambda unitized factor loading exposure to the shock. So this right here would be like macro shocks. And okay, in the factor model, Russell and Taha, you've got three parameters. Well, you got four parameters that are, well, no, you've got three parameters and you've got three random variables. So you've got random variable, random variable, random variable, right? So this is like transitory shocks. They're just like at the unit level. They're not really seasonality. They're just like, a local event that occurs at a point in time and, causes Y0 to fluctuate. These are hitting everybody. This would be like a recession or something that's hitting globally all the units the exact same. So it'd be a year fixed effect. So what are these? These are probably what you mean by, well, the seasonality might be this. You have to think about it. But these two things right here are unique time. So lambda t, okay, lambda t is a set of factors. I find all this language a little challenging, but lambda t is a set of factors that happen at time t. It could be a macro shock, but what it does is it's impacting each of the units in a different way. I'm not sure I understand what that means, Russell. More pre-treatment data? More pre-treatment data in the synthetic control context is used to model this right here as opposed to that. What you're trying to do in the what you're trying to do in the the synthetic control is the more time that you have, the more, since these on average are 0, the more time that you have, you're able to capture. I mean, maybe that's what you mean, that with more time, you're fitting the model off of this and not that. Okay. So I don't know if that would be the right way to call seasonality, but it would be a way of saying, I've got all these unobserved shocks that happen all the time. Okay. And I've got, 2 unobservables in the data. I've got the error term, which is unobservable. And then I've got this unique individual level unobservable feature, right, that responds differently to macro shocks. And I need the only structural part of the model is these 3 things. This is just noise. This just cancels out. But in a short panel, the weights are going to respond to units that have similar levels of noise at a point in time. You're wanting to find units that have similar levels of U, okay? And a longer pretreatment time series allows the model to kind of pick up and say, well, this is how I think of it. Well, these units are responding repeatedly in very similar ways, and this error is just kind of canceling out. So more data pre-treatment, I guess that would be here. But the thing is, you're not controlling for seasonality effects. You're finding groups that are responding to macro level or, global shocks. They're responding to them in the same way. It's as though they have the same U, right? It's as though they have the same U. So you found that unit that's got that same unobserved heterogeneity. Thousand data points by day for 3 years as opposed to 3-year units. Yeah. I would think that 1,000 data points by day for 3 years as opposed to 3-year unit. I mean, you're not allowed. It's illegal to do it off three-year units. You're not. I don't know exactly. There's not like a number where you can say that the minimum number of units. You just have an asymptotic argument as t goes to infinity, and 3 is too small. 1,000's better. And then, then you're going to be dealing with the fit, probably. I mean, honestly, like all these things, everything in the class is there. You're just dealing with all these diagnostic kinds of things you're going to do. You're going to be trading off one problem for another. So when you're going into that level of the 1,000 data points, the smoothness probably is not great. The smoothness is not great. And so you're going to get highly volatile series coming from these transitory shocks, I bet. But so the quality of the fit at the daily level, I don't have off the top of my head a paper I'm thinking of, but fitting off of that, you'd have more confidence over 1,000 data points or 500 data points. Maybe you don't need it that. Maybe you don't need 1,000, since like the most I've ever seen is like my paper that had 50. So you could maybe do a year, half a year, something like that. But I guess if you're wanting to kind of say these guys are similar throughout the whole year. Yeah, the U, Ronald, the U is at the individual level. So it's state. there's 51 U's. The T is the macro. It's almost like the T is like a, it's like, this is how Scott Cunningham responded. Yes, then that's right, Russell. Then that's right. The longer pretreatment time series will always give more confidence. It just might be that you have trouble getting a good fit, getting a good fit. That's the issue. The more the bigger these transitory shocks are, it just gets harder to do it. But yes, and Ronald, so you can have, yes, you have more than one U. These are panel U's. Each panel unit has some unobserved heterogeneity that responds to those unique events that year. And this right here, this lambda T, is not the same thing as that. This is like this would be everything else this would be a global, affecting everybody the same. And this would be the things that affect, like, so Ronald, say that this is your unobserved heterogeneity. Let's say that this year was great because you happen to own, in the stock of that, what's that GPU, Inveti? You own stock in Inveti this year, and I didn't, right? And so your like response, is like to that global shock is gigantic because of that unobserved heterogeneity that you had. Whereas to me, it didn't really do anything. I mean, it did something because I have everything, I've got savings, but whatever. But I didn't bet on that one company, right? So this is one for each. And what you're trying to do is you're trying to fit on this. But see, the T's are happening both at the same time. So you need more time to be sure that you found somebody that's got that your weights, those control group weights, have actually matched to units that are like also holding these really valuable stocks. I just made that up. But does that make sense? Okay. Um, okay, good. So that's what we're trying to do. That's why you need the long pretreatment time series. I mean, diff and diff does not need a long pretreatment time series. Diff and diff literally needs one baseline time series. Diff and diff is literally 4 averages and 3 subtractions. Y'all maybe have heard me say that before. It's 4 averages, 3 subtractions. The long pretreatment time series is used to construct an event study that gives you confidence that parallel trends holds. Or if you're using a regression model, you'll get more power and you can get smaller standard errors. But diff and diff is just, using parallel trends. This thing's a wild animal. That's not what this is doing. This guy is trying to find units in the data. It's matching. This is trying to find units in the data with the same factor loading. And it needs a lot more time to observe it. Shouldn't have gone this way. Needs a lot more time to observe it. Oh, I didn't even do it right. It needs a lot more time to observe it to really figure it out. Because at any one point in time, where did it go? Never should have left. Oh, at any one point in time, you're not going to be able to distinguish it. In synthetic control, here, let me put all these up. These are great questions. So in synthetic control, the number of control units is as important as pre-period times in order to get a good fit. So that's something that Abity talks about. Let me pull it up. I can't say it better than him. Whoops. It's in his 2021 Journal of Economic Literature. Okay, he's got a lot of tips in here. I think this is the one where he has the tips. He talks about control group units, donor. All right, let's see where he gets it. Sorry, I want to find it. Here we go. The risk of overfitting may also increase with the size of the donor pool, especially when the time period is small. For any fixed time period, a large number of donor pool units. Let me real quick this. I'll put this over here. For any fixed time period, a larger number of control group units makes it easier to fit pretreatment outcomes, even when there are substantial discrepancies in factor loadings. That's this, factor loadings, right here. Okay, so there's large differences in the factor loadings. Consistent with this argument, the bias bound for the treatment, that's the ATT, the bias derived in Abity, Diamond, and Haymuller, which is right here. This is the bias. Depends on J. Under a factor model of Y0, a large number of units in the donor pool may create or exacerbate the bias of the synthetic control estimator, especially if the values of mu J, that's this, in the donor pool differ greatly from the treated unit. So if you have a lot of heterogeneity in this right here, the factor model in equation 10 should be only as an approximation to a more general nonlinear process. If the process that determines it is nonlinear and the attributes even a close fit by a synthetic control, which is a weighted average, could result in large interpolation biases. Previous implication of the discussion in the previous paragraph is that each of the units in the donor pool have to be chosen judiciously to provide a reasonable control for the treated unit, including in the donor pool units that are regarded by the analyst to be unsuitable because of large discrepancies in the values of their observed Z, or because of suspected large differences in the values of the unobserved U, mu, is a recipe for bias. In particular, the value of the bound increases with the number of, yes, but he's not really given a ton of guidance. He's just like saying, don't put in there units that are really different on observables or your own hunch about these mu J. I would feel a little nervous personally, but I've never really worked with anything that's more than 50 states. I bet when you're working with countries, it really does probably begin to bite a little bit, but this is a good paper to read, Eduardo, to kind of get a little bit of the intuition. But the bias that they have worked out, where was it? Equation 10 here. This is this. Where was that bias? Does he actually write it down? Okay. Well, so those are things to be thinking about. I don't feel like these slides are as good as I want them to be, but that's the best I can do. So this is the synthetic difference in differences. Um, Susan Athey and Embens wrote that synthetic control is the most important innovation in causal inference of the last 15 years. And to prove it, they have written 2 papers extending it: matrix completion with nuclear norm regularization, and this one, synthetic difference in differences, which came out 2 years ago, I think, in the American Economic Review or JPE, something, one of the two. So synthetic diff and diff bears a lot of similarities to the matrix completion, because you're going to have this like low rank matrix, but you're going to be you're going to be focused on estimating weights this time, not the matrix. So this one seems to be getting a little bit more use for some reason. I'm curious. Let's see what it is. $708 sites versus that other one, which is whatever, 100 and something since 2021. And matrix completion's got 644, which was also published in 2021. So these are getting a little bit more use. You know, do with that what you want. So but there's some similarities. It's a little bit overwhelming, and I've taught this before where I go into way too much detail. If I'm going to try to get the high level and move a little faster, like all the others, okay, like all the others that we've looked at, what you're doing here is you're trying to improve upon Abity, Diamond, and Heymüller. And how can you improve upon Abity and Diamond and Heymüller? It's perfect. How can you improve on it? Well, you're improving on it when you have imperfect fit. Okay. And there can be situations where you just simply cannot, there's going to be situations where you simply cannot get good fits. So in some ways, what I don't really know what to do with is, like when we go back to this paper here, this one here, he likes just listing everything. Okay, this is from the Embens review article of causal panel methods, and he's like is he gonna, what's he doing here? 731 732. What is this? Hybrid methods. 2 recent methods combine some of the benefits of synth with either two-way fixed effects or diff and diff, or they do it with unconfoundedness. Matrix completion is with the unconfoundedness. So I think if we go down, we'll probably see matrix completion right there. Right? We do it. Is there a 4th one? Selection mechanism. Oh, simulation comparisons. Synthetic diff and diff outperforms. All right, so yeah, that's interesting. So I would love to dig into these simulations. So you've got basically like several hybrid methods, and they're all kind of being used in similar situations. All right. And synthetic diff and diff says here, they are being able to accommodate more flexible outcome models. They are, in essence, 2 approaches. One directly generalizes the outcome model, or one uses a local version of two-way fixed effects. somewhat similar to the way one can generalize a linear regression by making the regression function more flexible through the inclusion of additional function of the regressors, estimating local through kernels. So you've got here synthetic diff and diff, augmented synth, and then matrix completion. It's funny how he does it in 2 slides and I did it in a million. All right, so really the only thing I think, is when people are asked, like, which do you do? The only thing I really notice any of these guys doing is simulations. They constantly have them. That's how they're sort of trying to advance that one is better than another, is through these simulations. But those are based on specific data generating processes. And, you try to get as many as you can and have them be as generalized as possible. But so I don't know if that means, I don't know when he says that, if that means it's literally going to dominate every one of them. But he says, it's generally doing well. So recall that we needed good fit. The reason we needed that good fit was because the weights it's not that the weights are not the factor loading, but the weights go to units that in aggregate, we have modeled the factor loadings in the weighted average, okay? Even though the fit is imperfect for various reasons, often though the fit is imperfect, we've said that, and that happens because the weights are constrained to be non-negative, sum to 1. So that can be problematic. So what they're going to do is they're going to allow for an intercept. So that Duchenko and Imbin's paper is kind of showing up again here, where they're allowing for a constant level shift, but there's going to be more to it than that. So here's diff and diff, parallel trends, pre-trends. Recall what you need in diff and diff. You need parallel trends, untestable. In the smoking example, apparently when you looked, parallel trends didn't hold for many states. Choice of the control units matter. The average trends for many control states are roughly parallel, but not all. So a lot of this is review. Abity, Diamond, and Haymuller, what they did was they sought a weighted average over the control units to recreate the pre-trend through a fitting exercise. And then synth became the weighted average of the controls. And then the focus was just on estimating weights. All we ask is that the weighted average looks like the treatment group in the trend. All right. So Duchenko and Imbin's note that the synth weights are based on this vertical regression. And they yield coefficients on the control units as opposed to the lags in T. Somebody had said it earlier, when you have a longer T, your horizontal regression is getting more information. When you have a large N, that vertical regression is getting more information. To the degree that the fit pre-treatment is good, the gaps post-treatment are providing credible measures of average causal effects, okay? And, the weights, this actually is not getting imputed. It's the weights that are getting estimated. And so that becomes imputed, but, you're not actually messing with anybody's actual outcomes. You're just weighting them. So assume that synth at any point in time, assume that the synthetic control at any point in time, here's the treated unit, 1. Anytime you see that 1, it's the treated unit. At any point in time, 1, it's equal to the weighted average of everybody else. Synthetic control weights, W hat, control units to get weighted average controls. You use the pre-treatment data to find the optimal weights. And then when you aggregate over the control units, you get predicted treatment group outcomes. That's called fit. It assumes there's a stable relationship over time because this is going to be our estimated counterfactual post-treatment. So if you've got these weights that you based on pre-treatment, you're assuming they still work post-treatment. All right. And that's why it's really important to have a long pretreatment time series. It's not just so that it looks good. You need that long pretreatment time series in order for it to be stable post-treatment. And the only reason it's going to be stable post-treatment is if you assume that factor model is what's generating those potential outcomes. And that factor model has that lambda t ui, and you've matched on units such that on average, you've got your lambda I equals the weighted average of all those other lambda I's, even though you can't see it. That's how you know it's going to be stable over time. You need that lambda I to not be, you need that mu I to not be changing. Okay. And that's equivalent to the vertical regression. Doing all that is equivalent to the vertical regression. You regress the units against the higher column units to get those weights. I guess Duchenko and Embens figured that out. And it can require regularization in the regression if you have more units than you have time periods. Somebody said this earlier, forecasting. Forecasting is another way. So forecasting is also what synthetic diff and diff is going to be doing. Forecasting was also what matrix completion was doing, but matrix completion was never estimating weights. Matrix completion was estimating a low rank matrix. And that low rank matrix was equal to the missing counterfactual. All right. This time it's going to be getting weights. So you got going up and down, getting control group unit weights, and then going left to right, getting these time weights. And these time weights basically are weights on years that are best predictors of the post-treatment potential outcome in the control group, not the treatment group, because the treatment group in the post period is treated. So it's like it's contaminated. So you're going to use the controls to learn which of the periods would, be really influential in forecasting. So imagine a regression that yields coefficients on covariates, not the units, because the synthetic control is the units. Now we're getting it on the on covariates or something like that to predict future counterfactuals. It's just that what you're going to be doing it for is which of the years are highly predictive of future Y zeros, but only for the control group. Okay. You're going to need regularization if there are more time periods than units. And most of the time, every time I see this done, not surprisingly, it's the years just prior to treatment that seem to get the largest weights. Maybe, I guess like if it's very volatile, I guess maybe I can think of somewhere it's been very volatile and those have been a little bit more, you'll see weight further back in time periods that'll be influential, but most of the time it's not. So they will talk about diff and diff in the paper. They equate it with a two-way fixed effects model. I'm not positive. I'm not really positive, Ronald. They're literally going to be trying to, yeah, maybe. Huh. I bet so. That's got to be, that's got to be. It's the years, though. It's which of the years are, as opposed to the error, which is IT, it's which of the years are highly predictive of the future potential outcome. Those particular Y zeros are being highly correlated, very, very influential in predicting the future. But maybe thinking of it as autocorrelation is not the craziest thing. That's a technical term, so I'm not 100%. but maybe that's not the worst thing in the world to say. All right, so vertical regression, so reconcile. Vertical regression, that's scent. Horizontal regression, that's forecasting. Diff and diff is this. Yeah, yeah. It's the lag. It's got to be the lag. I keep thinking it's a time weight and not a lag. But if it is a lag, then you'd be getting a coefficient that's constant per lag. So yeah, that probably is right. So you've got a diff and diff. So three different things. The vertical regression is how you're getting the synthetic control. The horizontal is doing the is this unconfoundedness approach. It assumes a stable relationship between outcomes in the treatment period, the Y0 outcomes, I should say, in the treatment period and the pre-treatment periods, that that's the same for all the units. That's the one part, Ronald, I'm kind of just hesitating about, is that it's got to be the same for all the units. But diff and diff regression assumes an additive outcome model that looks like this, that captures differences between time and units. So the focus has been about choosing between these methods. Synthetic diff and diff is going to take the first two, all right? It's going to take the first two. It's going to do vertical regression and get weights here. This, all right? So it's going to do vertical regression, get weights, and it's going to get time. It's going to get the forecasting weight. So it's going to do both, get vertical regression, horizontal regression, get a synthetic control for that, and then do diff and diff. The last step will be to do difference and differences off of this. I think, I'll say this in a second because I might have it in here. So you're going to combine the two different kinds of weighting. Well, I'll say it right now. I bet some of you have seen this before, but it was not synthetic difference and differences. See, one of the things that you're getting with synthetic difference and differences is proofs, asymptotic theory, proofs that this works. Applied people, in my experience, have been trying to articulate something like this for a long time. I could be wrong, but that's what I have seen people do. They'll do what? They'll match units, treat a group to matched units. They might do a propensity score. They'll do some sort of matching, right? Once they've matched them, then they'll do diff and diffs. I've seen papers that do that. Those papers usually do not have any theory behind them. Alexa just said something. Don't have any theory behind them. Okay. So this has theory behind it. This is doing that thing, which I think a lot of people have, it's been building towards. Okay. So the focus is on getting appropriate weights. It's doubly robust. Also, only one of these weights has to be right. And that's another theme that keeps showing up more and more these days in diff and diff, as well as in these synthetic control things. We only need one thing to be right. We only need the time weights to be right, or we only need the synthetic control weights to be right. We don't need both. Any constant effects is going to be differenced out, and the synthetic control at that point will be parallel to the treatment as opposed to identical to the treatment. So that's what's going to be different. What's going to be different is this. So like, let's say historically, right, you had this right here. Okay, so this is like California. And what you did was you kind of did this. You got, you know, something like that, right? And that's like Synth, California. Okay. But notice it's sitting on top of it, right? It's sitting on top of it. When we were doing it before, we were like, I can't do it. I can't do it. I cannot. I've got this. The closest I can get to California is right there. All right. Well, it's gonna find these weights twice. It's gonna weight these units twice, and then it's gonna create this thing that is like, and I can't really do a good job here of it, but it's going to create a thing that looks like it. It looks like it in the trends as best it can. All right. It looks like it in the trends as best it can. And then what it's going to do is this. It's going to go after minus before. And it's just going to use the trend. And then this right here is going to be the treatment effect. That's going to be your treatment effect. You're going to go do the best you can. You're going to do the best you can. You're going to allow for this intercept. You're going to do the best you can, get those weights. And then once you find your best one, you do diff and diff. You do diff and diff last off the match sample. So constant effects are going to get difference out. Synthetic control can be parallel to treatment. Does not have to be identical. Doesn't have to be identical. So here's how it goes. Synthetic diff and diff is just diff and diff with a synthetic control and a pre-treatment period. All right, just like Callaway-Santana. So you're going to compute this regularization parameter to match the size of a typical one period outcome change. Estimate the unit weights using the pre-treatment data, but they're going to allow for the intercept term. So there's the intercept. So now the weights don't have to make since you allow for this, these no longer have to be like, they're not, since you allow for this, the algorithm is no longer like forcing the best fit on that. It's forcing the best fit on the whole thing. Okay. So you can have convex hull fail. You can have it be a bad fit. Then you're going to estimate the time series, time weights, using a synthetic pre-treatment period on the control data. And then you're going to combine them. When you combine them, you're going to run a weighted diff and diff regression. Okay, so you're going to actually run this regression. You've already estimated these weights right here. All right, so now all you're doing is you're weighting each of the units and you're weighting the time periods, and then you're running a two-way fixed effects model. Minimizing, there's your coefficient. There's your coefficient on W. You always know it's Embens if his treatment indicator is a W. So you're going to do that. You're going to estimate mu, which is the constant, alpha, which is the fixed effects, beta, which is the year of fixed effects, and then, that's the data. And then estimate the control weights. I thought I already did that. Oh, I think I duplicated it. That's it. I don't know what this is. So we already did that. So skip 5 and 6. So we did that. So more formalization. You're assuming this. You're not assuming a factor model. You're modeling the outcome. Okay, you're sort of assuming the outcome follows a low rank matrix, treatment, and then this matrix error. Okay, but we're not going to estimate that. Treatment can't depend on the error term, may depend on the systematic elements of L. So think of L as the signal. This is a matrix of treatment effects. E is the noise. No autocorrelation over time or between units. Okay, so the only thing random is the error term. So you modify the synthetic control weights, estimating the weights. You're going to use this penalization. So Abady's the only one who doesn't penalize. He puts restrictions, but he doesn't put a penalty term. So they're gonna use a penalty term. Use penalized least squares to get a weighted average of control group units with pre-trends that are parallel. They don't have to be exact. They just got to be parallel to the treated unit average. They're going to allow for a constant. They'll do the same thing with the time weights, but this time they're not going to regularize the time weights because they don't want to wait. They want to wait more intensively the periods just before. And if they used a penalty term like ridge, it spreads them out. So they don't regularize on the time. And so there's these oracle weights. I might skip these oracle weights. So here we go. This picture I got from the paper or from a talk that they gave. Here's omega. The omega is the W weights, okay? And then the lambda is pre-treatment control predicting post-treatment here. And so you're sort of this kind of visual of what you're doing. You're finding control group units that look like the treatment group units, and you're finding time periods that are predictive of the future. We were never with Abity and Diamond and Hamuller, we were never going over here. We were only in the past. This is the first time we're finding years that are predictive of the Y zeros. We're just using the control group to do it. We use the control group, and then once we get the control group, we do it also to everybody. So synth, just that. No unit fixed effects. No unit fixed effects. No intercept. Diff and diff. No weights. Synthetic diff and diff has the unit fixed effects and the time fixed effects. Inside is a two-way fixed effects model. On the outside are these two weights that we're estimating. And I've kind of now starting to repeat myself. So this is why I felt like these slides aren't as good. I feel like I repeat myself too much with it. So they have formal results. This is what gets it into AER, is the asymptotic theory. So they've got formal results that shows synthetic diff and diff is doubly robust. Doubly robust means you just need one of those to be right. Number two, factor model on the outcome can be a latent factor model. True model, still going to be consistent. They're basically showing that, your factor model can kind of be of different forms and it's still robust. As opposed to diff and diff, which is like only for parallel trends, they're kind of finding some of these synthetic control models are finding that it holds for multiple kinds of data generating processes. They're showing that it's normal, asymptotically normal. All right, so that's another big one. Oracle weights, synthetic diff and diff is going to have something called good weights. And then they're going to do inference through resampling methods like the jackknife, bootstrap, or randomization inference. And this is what it's going to look like. So here's a diff and diff. Notice this is just the raw data right here. They pick some baseline. They're picking some time period right here. I don't know why they picked this, but they start here. They go, here's the control group, straight line. This is what did happen, but I'm going to assume it would have followed that. That's my average treatment on the treated for that year. And they estimate that to be a negative 27.3. They just probably ran two-way fixed effects or something to get that. Synthetic control, this is hilarious. They said that it was a bad fit just prior because the weights are fitting everywhere. And, this is like, to call that a bad fit is hilarious. So, I've never ever gotten something like that. So anyway, I should probably be doing synthetic diff and diff if that's what they're saying. Anyway, here they go. Bad fit just prior because the way, they're saying it is a bad, it is not as good of a fit. And the reason is because it's weighting everywhere, all of them by that single weight. And then they do it and they find a average treatment effect of around negative 20. So had been negative 27. Now they find negative 19.6. And then they do their synthetic diff and diff. And here down here is their weights. Now notice that's synthetic control, that's synthetic diff and diff, that's unweighted. All right, so that's just like a normal diff and diff. Synthetic control creating an aggregate doppelganger. This is also a doppelganger. This is equal to W hat tau hat. So this is weighted. And then once it's weighted, then they do diff and diff. So they go, it fell by that much, it would have fallen by that much. And in this case, it's a smaller effect. The jagged line left of 1988 is weighting those years. So basically what this is saying is that in that weighting term, when they're forecasting, they're placing a lot of weight on the just prior to treatment thing. So practical problems, underfitting. What if I can't get a parallel synthetic control? Well, you'll know that you can't because you'll see it. So that's an underfitting problem. We need more controls. We need better controls. We need another method. So if you do not get a parallel synthetic control, you know, you have reasons to think that this is probably not going to work for that one. Omitted variable bias, something else happens exactly when the treatment occurs. You know, nothing gets rid of omitted variable bias except for getting the omitted variable. So there's not a solution to that. It's not, you're not identified. And then overfitting. We get a synthetic control because, but it's because the plot overfit the data. That means you're not approximating the counterfactual post-treatment. It's no different than in regression discontinuity design when you're unable to identify the counterfactual because of some functional form thing. So their estimator, this is where it gets deep. Their estimator is equivalent to an Oracle estimator, cannot overfit. So that's where this issue of overfitting, they address it with something called Oracle weights. Oracle weights are going to minimize the mean squared, well, weights minimize mean squared error. Oracle weights minimize expected standard error. They use time and unit weights that don't depend on the noise. So you have here your synthetic diff and diff. You have the truth. So this is the bias of synthetic diff and diff. And here's all the bias right here. Okay, so you've got some noise from an oracle. You've got some confounding bias. And then you've got some deviation from the oracle. And they characterize each of those terms. So first they've got this oracle noise. Tends to be small. So these are like, this is always here. They're just going to say that some of these things go to zero. All right. So first, the oracle noise tends to be small when the weights are small and there are a sufficient number of exposed units and time periods, meaning a large number of time periods, number of exposed units. I think that means donor pool units. Second one, Oracle confounding bias. Oracle confounding bias, the second one, the B. It'll be small when the pre-exposure Oracle row, number of units, regression fits well and generalizes to the exposed rows. So if this right here is that looks like there's your intercept and there's your weight on it. If it fits well in the pre, then the Oracle confounding bias should be small. That's on the unit weights and that's on the time weights. What if neither does well? What if neither does well? So if neither model generalizes well, there's a doubly robust property. It's sufficient for one model to predict the generalization error of the other. So the upshot is even if one of the sets of weights fails to remove the bias from the presence of that matrix, the combination of this Oracle weight can compensate. I think the main thing you just want to realize is that there's this doubly robust property to this. Core theoretical claim, this is all formalized. Synthetic diff and diff will be close to the Oracle when these time and unit weights look promising on their respective training sets and the regularization is not very large. So then, under some assumptions, they show it's unbiased and it's normal and it has a variance that's optimal, and you can estimate it with bootstrap, clustered bootstrap. So big picture, they do a simulation to evaluate the bias, the root mean squared error of the estimates compared to the observed outcome, but they don't want to use randomization. They may not catch the distinct time trends. So they want the simulation to be realistic, not ideal. So what they're going to do is they're going to use a paper. So this is this placebo simulation. So they're going to use this paper by Bertrand et al., and they're going to randomly assign a set of states in that data, the current population survey, to get a fake treatment. So there should be no effect. And the rest are going to be the control. This is something that people will do. First time I saw it done was Jeff Smith and Petra Todd did it in their 2005 paper, where they just basically randomly assigned units to be in the treatment. You know they're not treated, so your estimator better find a zero. So that's what they're doing here. And they don't want to do a simulation. So they want it to be more realistic. That just gave me an idea for all that matrix completion stuff. Okay, so to a placebo treatment, the rest of the control. Examine how well different approaches to inference for diff and diff covered the true effect. Only methods that were robust to serial correlation attained valid coverage. So they have some policies they're going to look at. Policies on abortion laws, policies on gun laws, policies on minimum wages. Okay. And this is how they're going to do it. So here we go. I don't want to get into this. So compare, I just want to get to the simulation. Let's see what it does about, but here we go. Synthetic diff and diff, two-way fixed effects, synthetic control, matrix completion. So the two big ones are synthetic diff and diff and matrix completion. It would have been nice to see some of this augmented synth. That would have been nice. I don't think that's in here. So this is the distribution of the errors. Red is diff and diff. Green is synthetic control. Synthetic diff and diff is the blue. This is minimum wage, random assignment. All right, so under random assignment, we're getting a smaller variance than we're getting with diff and diff. The bias. Here we go. So synthetic diff and diff in the baseline looks like the bias is the smallest, diff P. Diff P. I cannot remember what diff P is. Here, outcome model, no correlation. So there's these different kind of things they're doing in their simulation. Let's look at the actual one, though, with the laws. So here you're getting a bias of 0.08. Synthetic control is getting a negative 0.03. Diff and diff is getting 0.15. Matrix completion is getting 0.15. So these two are pretty similar. On the abortion paper, it's a bias of 0.04. They know the bias because they've randomly assigned abortion laws to states that don't have them, so there should be no effect. 0.04. 0.16. So here you're seeing, here it's not the lowest one. It was the second lowest. Here you've got these others that are a little bit less biased. They're focused more on root mean squared error. Outcome variable for the minimum wage, hours. Yeah. So let me see the sum of you. So the inference, they're going to do these. All right, I'm going to skip this. So some practical considerations. More treated units is worse. When we add in more treated units, it makes the oracle standard deviation decrease faster. So circumstances are ideal if the signal matrix admits a good oracle. So what's good? Oracle control weights distribute mass over enough control units. All right. So I want to get, so here we go. I want to get, so some comments. This is ADH, so this is conceptually, this is synthetic control combined with a simple 2x2 and an intercept. The weights are based on time and control group weights. The Oracle weights job is to make sure you don't have overfitting. And synth diff and diff dominates synthetic control without any negative weighting. Still remains to be seen how we're going to go about choosing between them, but some things we may need to just put down. So we have code in Stata called synth diff and diff, and I believe we have it in R also. But I want to show you a paper. I believe this paper might have just gotten published. It's a null result, but here's how they wrote it. It's Victor Mello, Elijah Nielsen, and Dorothy Kimbowie. It's a 2023 working paper. They wanted to know the effect of indoor vaccine mandates in U.S. cities. They wanted to know what was the effect of a vaccine mandate on allowing you to go to the movies or allowing you to go to restaurants. It was these indoor, like allowing people to go indoor, you had to be vaccinated. They couldn't require you be vaccinated in the United States, but they could require you be vaccinated. Certain cities could require you be vaccinated if you went to the movies or went to a restaurant. And so what they want to know is, well, what's the effect that it had? City level vaccine mandates. They're going to look at COVID-19 cases, deaths, and vaccine uptake, and they're going to use synthetic diff and diff. They're also going to use synthetic control, and they're going to use diff and diff, and they're going to find no effect on anything. So if you're finding a null effect, I guess it might be good to show this. So many policies taken, obviously, we all remember this. Many policies were taken to incentivize citizens to get vaccinated, including lotteries. And one of them was, you had the carrot and you had the stick. And so the carrot would be the lotteries and the stick would be punishment or restrictions on your movement. So, and one of the most restrictive was just preventing people from entering public places, theaters and restaurants without proof of vaccination. Many large cities implemented it to try to get vaccination rates to go up, to try to get COVID cases to go down, to try to get mortality to fall. Problem was many Americans refused to get immunized. All right. In February 2021, 30% adults said they definitely will not or probably will not get vaccinated. So you had these low vaccination rates led to measures to increase uptake here. These low vaccination rates were what led to these policies. So when the Delta variant came out, New York City passes in August 3rd, 2021. They pass mandates, proof of vaccination to go into restaurants, concerts, stadiums, and gyms. And then other major cities do it too. So here they go. You got an announcement date, you got an implementation date, and then you got a repeal date. So it's staggered. All right, staggered. They're going to do it though one at a time. You could have done augmented synthetic control, staggered rollout. They could have done that too, but they're going to do synthetic diff and diff. You could have done matrix completion. They're not going to. They're going to estimate an average treat on the treated for each state or each city rather. And the data is going to come from county level COVID-19 vaccination cases and deaths. They're going to aggregate to the weekly level. So they're going to have a weekly panel from December to April for 821 MSAs. They know they've got various issues with data quality. So they drop around 100. They end up with 57,470 observations. Some descriptive statistics. They've got about, this treatment group, control group. You can see the treatment group has more first doses than the untreated cities. I think that's not surprising. The treated cities have about the same number of cases, a little bit lower. The treated cities have lower deaths than the untreated cities. And then that's it. It's always good. What I've noticed now is this has become the dominant, maybe y'all know this, but this has become the new table one. Everybody, treatment group, control group is probably what you want to do. The referees are going to ask you to do it if you're not already doing it. They have a nice paragraph. So for those of you that have been a little lost, here we go. The basic idea is that the unit weights are chosen to find a convex combination of potential control states. The inclusion of the intercept term, made possible because of the inclusion of the unit fixed effects, is one way in which this differs from the synthetic control weights. So these will not be the exact same weights. Okay. And because they got these unit fixed effects in, is the reason that you are not laid on top of the treatment group. Instead of the weights needing to make the pre-trend control unit perfectly match that of the treated unit, they allow for this intercept, makes it sufficient for the weights to just make the trends parallel. So they do diff and diff, two-way fixed effects, by city, synthetic control, synthetic diff and diff. And they use placebo variance estimation to get these confidence intervals. So you would want these things to be positive. What you're wanting. Is it causing an increase in first doses? So positive, 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 positive. Most of them are not positive, positive. So, it would have been nice, I think, now that we've gone through this, to kind of think about this pooled approach. Here you've got a bunch of individuals, but we're not looking at how good the fit is on these synthetic controls. So it's not really clear if we should really believe this. If I could pause for a moment. Writing these new papers is going to be a chore. There is no formula to follow. You're going to have to go back to the basics to really figure out how do you communicate this to people without overwhelming them. Okay, so they chose to do it this way. Synthetic diff and diff, if we look at the confidence intervals, all right, even on these positives, they're huge. Nothing is significant. I don't think, anyway. Let's see. Is anything all negative? That's close. That's not even the right sign. Nope. So that's first dose. That's cases. And again, you want negatives. So Los Angeles gets a positive. I would love to see that Los Angeles diff and diff, but it's the only one. So, nothing's coming in. And then they look at deaths. You would like these to be negative. One is San Francisco. And again, you would like to see that diff and diff. I mean, you would like to see that synthetic control. Now, what they're going to show is the synthetic diff and diffs. They're going to show the synthetic diff and diffs. So they make them. Which one did I say I liked? San Francisco on mortality. Yeah, well, that's not the synthetic control, though. So let's look at these. How do you interpret these? So the interpretation is off of the dashed line and the blue line. The blue line is the treated. The dashed line is the imputed counterfactual off of a diff and diff. So that's teeny tiny. Boston has a slightly positive effect on first doses. Let's look and see. It should be very small. 319. No, here it is, 72. So it's very small. You can see. So what they did was they've got a table of results with confidence intervals, and they've got a visual also. So these are, the synthetic diff and diffs. Some look better than others. And they just don't ever seem to find consistently very strong evidence for it. So the way they go about it is they report 3 models, different, and again, it's this thing that we've been seeing. It's this thing we've been seeing more and more, which is things like this show multiple models. Okay, so they show the set and the diff and diff, and they're showing all of them. So that might be something to keep in mind. Historically, what would we do? We would do 2A fixed effects. It was one model, and we'd put in controls, or we put in different kinds of fixed effects. Now it's a bunch of different models, but they fail to find strong evidence that the vaccine mandates slowed COVID-19. So I see some people typing, so I'm going to skip over here. So the treatment effect in the synth diff and diff did not show us the final date in the data. Just find an appropriate date and pre-treatment appropriate date. Yeah, exactly. I mean, there's nothing that would stop you, Taha, from creating an event study and like getting it, for all of these periods. But they're basically calculating, what I believe they're calculating is a mean post-treatment and a mean pre-treatment. I think it's just a simple like pre-treatment, post-treatment average. And I think that's like what it's doing. If you wanted to do an event study, you could. Yeah. Yeah, you could, Dongley, and that would definitely violate SUTVA if the neighboring cities are in the control group. So, if you are, so yeah, that would be part of the treatment effect, I think, though, because that would be basically finding. I mean, I think that would be part of the treatment effect. You just would want to make sure that your control group is not contiguous. Probably, if you suspected that, make sure that you have a donut around the control groups, then redo it. But if they're moving away, then that's the result, which is they didn't get their vaccination. Okay, so that's part of your result. I'm going to do the concluding remarks, unless people have more questions, because I think doing an event study from finance might be murder, especially since we only have 23 minutes left. So I just want to tell you a little bit here. Here's Abity on the value and the use of synthetic control. Synthetic control provides many practical advantages for the estimation of the effects of policy interventions and other events of interest, which is probably everybody on the call. That was like why they came. They're wanting to study policy interventions at an aggregate level. However, like a country or a state or a firm or a school, It's not really, if you're trying to estimate the returns to a college education, this doesn't make as much sense. But for aggregate interventions, it makes sense. However, like for any other statistical procedure, and especially for those aimed at estimating causal effects, the credibility of the results depends crucially on the level of diligence exerted in the application of the method and on whether contextual and data requirements are met in the empirical application at hand. So synthetic control was developed for the comparative case study. It's a type of matching estimator with an underlying factor model for its identification. Advancements have been made along multiple dimensions. Bias adjustment to deal with the imperfect fit, demeaning, including intercepts, as well as exploring more general structures than just these factor models. It is now a robust general causal panel method. The assumptions needed to justify it, require some due diligence. But it's probably the case now going forward that we're going to start seeing it. We're going to start seeing it more and more now that it's moving beyond just the comparative case study. Okay. So the focus on the treatment assignment mechanisms carefully to help understand how unobserved time varying confounders can be threatening your results. Pay close attention to issues around observable matching bias. Remember the importance of the long panel. These are like things that you need to be keeping in mind. Remember that when you're using negative weights, you're extrapolating. So be a little careful with this idea of the bias reduction. Don't just do it for the purpose of fitting. Do it because you are willing to make that extrapolation. And that is it. That is it. So I am going to open it up to comments. If anybody has any questions. I know that was pretty intense. Even though we really only did a few papers, hopefully they were organized well enough that you can at least go back and sort of, you've got code to do these things and you can at least kind of bite off and know synthetic control, how does it fit? Look at the fit. If I cannot get good fit, willingness to go into augmented synthetic control, willingness to use matrix completion, all of these things at least have some basic rules. No, not yet. At the moment, it is the binary treatment. Continuous treatment is sort of the cutting edge of these panel estimators at the moment. You can like always have a continuous treatment and run a regression model, but you're imposing, when you do that, constant treatment effects. And, if you're not willing to do that, then you get into trouble. So no, it's not at the moment that I've seen. Well, guys, should we call it a day? It was a lot of material. I'm going to get this posted momentarily. And, I hope it was helpful. I hope the recordings will be helpful. And I hope that the code, should be adaptable. The only one we didn't really go through was synthetic diff and diff. But at the moment, the rest of them we were able to do and to explore a little bit. So I appreciate you guys coming and supporting the workshop. I hope it was useful. And I'm going to let you guys go 15 minutes early. All right. Okay, see you guys. Bye bye.